Okay. Brian, could you please make co-host to Professor Michael Rochansky?
Hello.
Hello.
Hello, Professor Michael. How are you?
Okay. Yes, okay, good. Yes, how are you?
Could you? Good, good. Could you hear me well? Right? Okay. Could you hear me well? Okay, let me see. I think the Professor Michael is.
Could you hear us, Professor?
Yes, yes, I can hear, yes.
Okay, okay. Could you
Okay,
hear me? Because maybe it's my microphone.
No, I can hear everybody.
Okay, okay, good, good.
Okay,
Okay.
Professor. Maybe you can try to share your screen, your slides.
Okay, yes, let me. Where is it? Oh, yeah. Wait, can you see or what the can you see it?
Yes, I can see. Perfect. Yes, I can see. Okay, okay, so I think we can start, right? So, Professor, first of all, thank you very much for accepting our invitation. Okay, so, okay, our next speaker to start the last day of our conference, ICMAM Latin America Conference, is with the Professor Michael Rushansky. So it's my great pleasure and distinct honor to introduce Professor Michael Rushansky, one of the world's leading mathematicians in the fields of non-commutative harmonic analysis, microlocal analysis, and partial differential equations. Professor Rushansky's academic journey is a remarkable example of intellectual excellence and international collaboration. After completing his studies with distinction at St. Petersburg State University, he pursued doctoral research at Utrecht University under the supervision of the legendary mathematician Johannes Duistermaat, earning his PhD with a thesis that made significant contributions to the theory of Fourier integral operators with complex phases. From there, his career led him through distinguished appointments at Johns Hopkins University, the University of Edinburgh, and Imperial College London, where he rose from lecturer to professor and continues to serve as an honorary professor. Today, he also holds the positions of Senior Full Professor and Senior Research Professor at Ghent University, while remaining professor at Queen Mary University of London. Through his career, Professor Rushansky has profoundly influenced modern mathematical analysis. His research spans harmonic analysis, microlocal analysis, pseudo-differential operators, Fourier integral operators, analysis on Lie groups, and the theory of partial differential equations, including hyperbolic, dispersive, Schrödinger, and evolution equations. His work has not only advanced fundamental mathematical theory, but has also provided powerful analytical tools that continue to shape contemporary research across several branches of mathematics and mathematical physics.
The international mathematical community has recognized these groundbreaking contributions through numerous prestigious distinctions, Among them are the Methuselah Laureateship, one of the Belgian highest recognitions for scientific excellence, the Odysseus I Project Award by the Research Foundation Flanders, two Ferran Sonjer First Balanger Prizes granted in 2014 and 2018 for outstanding mathematical monographs, the Isaac Award, the Daiwa Adrian Prize, the EPS RC Leadership Fellowship in the United Kingdom, as well as multiple fellowships from the Japan Society for the Promotion of Science and the Leeuwenhoek Trust. Beyond these remarkable achievements, Professor Ruchansky has distinguished himself as an exceptional mentor, collaborator, and scientific leader. Through his vision, he has built vibrant international research community, supervised numerous young mathematicians who now contribute across the globe, and foster collaboration that bridge continents and mathematical disciplines. His influence extends far beyond his own publications, leaving a lasting impact on generations of researchers and on the development of modern analysis. Today, we have the privilege of hearing from a scholar whose work combines extraordinary depth, originality, and lasting influence. His contributions continue to inspire mathematicians worldwide and exemplify the highest standards of scientific excellence. Please join me in giving a warm welcome to Professor Michael Ruchansky, who will talk about non-commutative Fujita exponent.
Okay, thank you very much for this kind introduction, and it's a pleasure for me to give a talk here. I was trying to prepare a different topic somehow, but then I got short on time, so I decided to talk to you about non-commutative Fujita exponent. So maybe some of you heard it before, then my apologies, but anyway, so this is the topic now. And so it's about non-commutative Fujita exponent, which means that well, we have Fujita exponent, which is a threshold for the well-posedness for semilinear heat equation with power nonlinearity, and then non-commutative here means that we look at it in different non-commutative settings. So the plan of my presentation is the following. I will talk about Fujita exponent on groups, rather general groups, namely unimodular groups, general unimodular groups, and Lie groups. And so we have an underlying group structure. This is problem one. Problem two that I will talk about is when we don't have group structure, but we have Hermann's system of vector fields, and we consider sum of squares of these operators. Then problem three is when we have concave nonlinearity, namely u to the power p when p is, for example, between 0 and 1. It's a concave function. And problem four is when we consider the setting of quantum torus or quantum Euclidean space. And okay, this part, actually, this is the one that I was trying to add slides about, but I think that I may, as I didn't have time, then I may just try to focus on the first three problems. Okay, so nonlinear heat equation, it's the following equation. As I said, it's a heat equation plus u to the power p. First, we look at the convex case, so p is strictly bigger than 1. P is equal to 1 is not so interesting because it's a linear equation. Then we have, of course, the global existence, but for p strictly bigger than 1, the Euclidean situation in Rn, this is a fundamental result by Fujita, who found this exponent here, pf. So n is the dimension, and pf, and it is a threshold for the well-posedness. So if p is less than this pf, then there are no global in time solutions to this equation. So all solutions blow up. If P bigger than this PF, then global solutions exist. We look at positive data always. Global solutions exist, and if P is equal to PF, this was the case was done after Fujita, soon after Fujita. In this case, so the critical index belongs to the blow-up regime. So in this case, we don't have global solution. So this is a very fundamental result, which is 60 years old now by Fujita. And since then, people studied this problem in many settings in the Euclidean situation. For example, u to the power p can be replaced by a function, f of u satisfying some properties. Laplacian can be replaced by nonlinear Laplacian. One can consider this equation in domain with different boundary conditions. One can consider this equation on manifolds, Riemannian manifolds, with different volume growth, for example, polynomial volume growth, with different assumptions on the curvature. So this problem has been studied. However, when I became interested in this problem, two observations became clear that in the setting of groups, very little was known. This is for this problem. And the second is this last line here. If you put function of t in front of u to the power p, then there are results, but again, Euclidean results, and what happens in groups, and then nothing was known. So this is the motivation for this talk, to understand, for this research, to understand what happens if you have groups and groups of different types, and can we produce some general results, or they may depend on the type of the group and so on. So just to remind you here, so a group, just to fix a couple of definitions. So the group is, we have identity element E in the group G, and we have two operations, a group operation and inverse operation, that fit to each other, like here, and we have associativity. We don't assume commutativity. If the group operation is commutative, then we have a commutative group, and a special case, so we don't assume it here. And a Lie group is a smooth manifold, which is also a group at the same time. And these two group operations, so the group operation and inverse operations, they are smooth with respect to the smooth structure of the manifold. Okay, so then what we have on such groups, if we don't need Lie group, assumption for the following is, if it's just a locally compact group, then there are also two measures. There are always two measures, left Haar measure and right Haar measure, which are uniquely determined measures, modular constants, multiplication by constants, which are invariant under shifts. So left Haar measure here is invariant under shifts to the left, and right Haar measure invariant under shifts to the right. So in general, these two measures are different, but they are uniquely determined up to constant. They give us integrals. Once we have measure, we can define integration with respect to this measure, and the integral again becomes left invariant to right invariant under shifts. And as I said, these two measures can be different in general, but if it happens that they are the same, then we call the group unimodular. Okay, so this is basically the only definition which we need here. And so examples. So there are many examples, like Euclidean space, torus, all compact Lie groups, Heisenberg groups, stratified groups, graded groups, homogeneous Lie groups, so nilpotent Lie groups. They are all unimodular Lie groups. So okay, so this is the groups which will be covered under in this work because we look at the unimodular Lie groups. Let me recall a result which I had with my former PhD student, with Cyrus Serkigenov, already a few years ago. We looked at the Fujita exponent for general unimodular Lie groups. We can assume it's connected. Otherwise, we may have results on different connected components. So it's not restrictive. We look at general unimodular Lie group. By definition, we have two Haar measures which coincide. So effectively, it's one Haar measure which is bi-invariant. So invariant and the shifts to the right and to the left. We take Hermander system of vector fields. So meaning that it satisfies Hermander conditions that iterated brackets of these Lie brackets of these vector fields span the whole tangent space. We have a so-called Carnot-Caratari distance, which means that we measure distance between points by joining them by lines, by curves, with the properties that tangent to this curve is always in the span of these vector fields. So such distance exists always, and it's called Carnot-Caratari distance. It is in general different from the Riemannian distance if you put Riemannian structure, because there we would allow any curves. Here we allow only so-called horizontal curves. So the tangent vector is in the span of these vector fields. Then we consider balls with radius r around a point V of r. It doesn't depend on x because it's a group. We can look at the volume of the ball, how it grows with respect to r. And sum of squares of these vector fields is hyperelliptic. It's sublaplacian, which is hyperelliptic by Hermander theory. So there are then the following properties that we have. First of all, for small radius, the volume of the ball always grows like r to the power d for some small d, which depends on the group and on the system of vector fields that we choose. It's called the local dimension. And for large R, there are two possibilities, and they depend only on the group, but not on the choice of the system of vector fields, which is nice. So either V of R grows polynomially, like R to the power d for some capital D, and then D is called the global dimension of G. So the volume growth. So this is polynomial growth, volume growth, or another possibility is exponential volume growth. So there are only so all unimodular Lie groups, they fall into these two categories, which we have to study. We have to look a little bit differently, because obviously as the volume grows influences what is happening at infinity. So this is the situation, and then so our result is the following that we had with Serkigenov in this situation. So we found Fujita exponent, and we found unifying formula for this Fujita exponent to be 1 + 2 divided by capital D, where capital D is global dimension. And a unifying formula in the sense that if we have exponential growth group, we can formally put capital D to be equal to infinity, then PF is equal to 1. And if it is a compact Lie group, then capital D is equal to 0. There is no volume growth, in which case PF will be equal to infinity. So there are essentially three types of groups: compact, when volume doesn't grow; second, when volume grows polynomially; and third, when volume grows exponentially. For each of these cases, we have capital D, and the formula is the same. So local dimension does not enter in this formula, as you see, but it is a global dimension. And the result, the theorem that we have here is in blue, is similar to the classical Fujita result. If P is less or equal than PF, then there is always blow up. If P is bigger than PF, then it is existence. So for example, compact Lie groups D is equal to 0, PF is infinity. So P is always less than PF. It means there is always blow up. There is always blow up on compact groups. So polynomial growth, there is Fujita threshold as before, and exponential growth when D capital D equals infinity, PF is equal to 1. So P is always bigger than PF. P is always bigger than 1. So there is always global existence. So this is results that we had, and then so just to, and for completeness, just let me mention briefly that we developed a certain method which actually allowed us to treat not only Fujita, not only this equation, but more general one. We can put a function f of u here, not just u to the power p, and then we have satisfying just inequality like this, or less or equals than u to the power p, larger or equals than u to the power p, and then we can look not just equations but inequalities. In the critical case, result is for the equality, but in the non-critical cases, we can look at the just inequality, and then not just equality has blow up, but also this inequality has blow up. Okay, so this is the situation here, and then this is polynomial volume growth, and then also exponential volume growth. We have also result for inequality. Okay, so problem one, which so this is an older result, and now I move to more recent result. So problem one is when we have a function phi of t that we put in front of f of u, and we want to see whether what can we say about global existence of this equation. And assumptions that we make on phi will be quite mild. Phi will be non-negative. Non-negative function, locally integrable later on, and f here, because we want to have interplay between phi and f, so we don't take u to the power p, not to restrict ourselves, but we just take a function f which is 0 at 0 and positive, and we look at the mild solutions here. So if there is a classical solution, then it's also a mild solution. So we look at the equation in this integral form. And again, we say that global existence if L infinity norm is controlled for all time, and but if L infinity norm goes to infinity, then we talk about blow up. So our results are the following. There is sufficient condition to have global solution, and there is converse, which is necessary condition, which we do for Heisenberg groups. And these necessary and sufficient conditions coincide for that we showed in our paper. It was known they coincide on Rn. We showed that they coincide in the first Heisenberg group, and but recently there is another improvement that is not published yet. I think it's one can show that actually we can find this necessary sufficient condition for any Heisenberg group, but I will not talk about this now. So some technical functions we defined, this minorant and majorant function. Don't worry about them. They will not enter much. Only we have this, they enter here in this condition. So, okay, it's a technical condition. For example, power nonlinearity satisfies this condition for p bigger than 1. So we don't worry about that so much. So G is a general unimodular Lie group. F is continuous. F is nonlinearity, 0 at 0, positive. We assume that this mapping is non-decreasing, but again, if you think of f of v to be v to the power p bigger than 1, then this is some kind of convexity assumption on f, and phi is non-negative locally integrable function. Then our theorem is the following, that if G, so first if G has polynomial volume growth, because in comparison with the previous result, when we had power nonlinearity and Fujita exponent, we could come up with unifying expression for the index, which contains different cases of groups. So here situation is different. We look separately polynomial volume growth, which contains the case of compact groups, because we can put capital D equal to 0. And then the theorem is the following. The first theorem is that in one direction, if there is no, so if there are no solutions, so if there is always blow up, then this integral here has to be infinite. Also, this integral has to be infinite, but this is harder to check. This is the first type of condition but it's harder to check because we have to evaluate f on some L infinity norms and so on. Yeah. Okay. Yeah. But this condition is easy to check because we just put phi and f, and for every theta we check if this integral is finite to infinite, and if there is blow-ups, then we know that it has to be infinite. So if it's finite for some theta, then it means that there is no blow-ups. It means that global solutions exist. And exponential growth here, we don't have capital D because capital D is infinite. That's why this condition, we don't come up with a unifying condition, because if capital D is infinite, we cannot use this formula. But then condition is the following, and here local dimension comes up. Interestingly, that this integral has to be infinite, but for all theta, but also for all nu bigger than local dimension. Okay, so this is implication in one direction, and corollary, of course, is by logical negation. If the integral is finite for some theta, then there are global solutions. So some consequences of this result. So if phi is equal to 1, so we don't have this function that we plug in there, then we can recover the just results of the Fujita exponent, because if phi is equal to 1 in this integral, phi disappears, and you put f of u to be equal to u to the power p. So then this will be raised to the power p. It doesn't depend on theta. Theta comes out of the integral. This is just condition on the power of tau for the integrability of this. And what we get there is exactly the Fujita exponent that we had before. So then, in this sense, it is an extension of previous results. Although not complete extension, because before in that paper I said our results apply to inequalities also. Here we just deal with equation itself. So Euclidean case was known by these guys, and we recover their result here, but we have also some minor improvement of their result, because they had more assumptions on functions on the admissible class of nonlinearities f. We reduce it, so they required some regularity of f, for example. We just need continuity of f. But in terms of orders, we recover that result. So if so as I said, if phi is equal to 1, f of v is equal to v to the power p. We have Fujita case, and we recover exactly Fujita exponent here. And for compact groups, when d is equal to 0, also you look at this condition, capital D is equal to 0. There is no tau here. It comes out. This comes out. And it's just condition on integrability of phi. So if phi is an L1, then there are global solutions for any nonlinearity. So remember, if phi was equal to 1, then we had always blow up in the compact case. If phi was if there was no phi, or phi is equal to 1, then there was always blow up. But now in that model, if we put phi which is an L1, then there is always global existence. So this is interesting to compare these two cases. Okay, so now I move on a little bit. I will talk about Heisenberg groups. Let me be very brief because I guess most people know what it is. So we have Heisenberg group, which is R2n plus 1. There is group law, which is not commutative because of this quadratic term, but identity element is 0, inverse is just minus the element. Again, we have Carnot-Carteret distance there, and we have dilation structure. Here we have, it's a homogeneous group, so we have dilation structure, which makes sub-Laplacian homogeneous operator, and which tells us that the global dimension is the same. The global dimension in this case is different from the topological dimension. The global dimension is just the homogeneous dimension, which is 2n plus 2. So as a topological dimension of the Heisenberg group is 2n plus 1, but the global dimension or the homogeneous dimension is 2n plus 2. So it's not a Riemannian manifold, sub-Riemannian. And so these are left invariant vector fields that we put here. They satisfy Hermann's condition about the commutators. So they generate so they generate sub-Laplacian. So we put here the horizontal gradient, and horizontal sub-Laplacian is sum of squares of these vector fields, and it's hyperelliptic by the Hermann's theorem. So it's a special case of the previous construction. So graded, stratified groups, let me skip a little bit here. So the conditions that I presented to you before was the following: that so the global dimension is, as I said, is the same as homogeneous dimension, is 2n plus 2, and so necessary condition for blow up. So the previous theorem which I showed in the case of the Heisenberg group, it says that if there is blow up, then this integral has to be infinite for every theta. And the converse theorem which we had in our paper was the following: that if this integral is infinite, then there is blow up. So it's in the opposite direction, but the orders n minus 1, n plus 1 here, and 2n, they're different. Okay, so this was the case. But before I discuss the difference in these orders, let me just give you small examples that you don't have to follow, but just to say that this condition is very easy, is checkable. For example, we put f is like this, sum of two non-linearities. We can put phi of sum of two non-linearities. We calculate this Majorant Maynard function. We check that conditions are satisfied, and the condition in the integral just reduces to gives us condition in P. So ideally, if we have like necessary and sufficient condition, for example, or just necessary or sufficient conditions, then by checking the value of this integral, we can find values of P and Q. Here, P is bigger than Q, so it's the bigger P which is responsible, and if it is smaller than this, then we have blow up. So these conditions are really easy to check. So on the Heisenberg group, however, H1, let me say that H1, the first Heisenberg group, is n is equal to 1, then what we have is n plus 1 is equal to 2, and 2n is equal to 2. So in this case, we found necessary and sufficient condition, which is formulated here, is that so there is blow up if and only if this integral is infinite. This integral, which is easy to check, is infinite. So necessary and sufficient means that if there is so global existence, so it's complete characterization. However, in so for other Heisenberg groups, these conditions do not coincide. And in the paper, we put this conjecture that it is this integral which is responsible. And I think now, so as I said, there is pretty likely that this conjecture is proved. And but I will not talk about this now yet. Anyway, so then I move to the next situation. The next situation is when we have, let's forget about the group structure now. This problem 2 is when we have Hermander sum of squares. So what happens in this situation? So let's say we are on Rn, we have Hermander system of vector fields, we don't have underlying group structure. So we can think of like Grushin operators. What happens in this case? So let me describe this setup in more detail. So we have Rn, but we allow not just, okay, Rn has a usual multiplication, has, no, because we don't talk about the group, it's just usual Euclidean space, but we put an anisotropic dilation on it to make it more, to broaden the class of applications. As I said, for example, model case is Grushin operators. So we have delta lambda, which is dilation map, which is anisotropic. So we have sigma 1 in the first variable, sigma n in the last variable. And we talk about vector fields. So vector field homogeneous of order L. If when we combine phi with this dilation map, we apply x and lambda to the power L comes out. So it means homogeneous of order L. And we start with a family of vector fields. So Hermander, so system of vector fields, which are homogeneous of order 1 with respect to this dilation. So they don't have to be homogeneous of order 1 with respect to the standard Euclidean dilations, but the homogeneous of order 1 with respect to this delta lambda. And second condition is Hermander condition. It's formulated here a little bit in a fancy way, but this is just Hermander condition that about these vector fields. We can reduce it to 1 point again if you want to check because of this dilation structure, but basically it is Hermander condition, so sublaplacian is hyperelliptic. And example which I mentioned before is this Grushin vector field. So let's say x1, x2 in R2, this gamma here. It is so gamma integer. So these are Hermander vector fields, but it's not elliptic operator, sum of their squares, but it's degenerate elliptic, but it's hyperelliptic by Hermander theorem, and these vector fields they are homogeneous of order 1 if we put if we choose these dilation weights appropriately. So these sigmas are dilation weights. Again, we have as usual we have no Cartesian distance here, which I will not define again, but the definition is written here. So tangent vector. So we connect 2 points x and y by curves gamma. We look at their lengths, usual lengths, and the property is that tangent vector to gamma is spanned by these vector fields here. We look at the balls with respect to this distance, and they have nice properties because we have dilation structure. So if we dilate points, then the distance dilates for the one. If we dilate the balls, then everything dilates as well. And what is important is that the measure, if you look at how the volume of the ball grows with respect to dilations. So if we put instead of radius r, we put lambda r, then lambda to the power q comes out, where q is the sum of these weights. So you see that this is a number. This will be the number actually important for the Fujita exponent, which is the sum of the dilation of the weights of this dilation. So if you're in the Euclidean case, when all dilations are standard 1, then all sigmas are equal to 1. In this case, q is just equal to n, the topological dimension. But for Grushin vector fields, for example, this q is different from 2. So Grushin two vector fields in R2, the q will be different, will depend on the dilations. On the dilations which make these vector fields homogeneous for the 1. Okay, so then we look at the heat equation. So we look at the heat Fujita exponent. So this is nonlinear heat equation. So we look at the heat operator. It has a heat kernel. So it has a heat kernel, and it has estimates. There are heat kernel estimates. This is known. Moreover, recent results by Biaggi and Bafaglioli that we base our analysis on give us, so it's a bit more properties. It's a global heat kernel, which satisfies all the properties of the heat kernel that we want. So it's, for example, non-negative, causal, symmetric in space variables. Its integral is equal to 1. And we have kind of semigroup property at T plus S. It's found from heat kernels at the times T and S. Okay, so then we look at the nonlinear equation that we're interested in for Fujita nonlinear equation, and then we look at the mild solution. So by Duhamel formula, U has this expression, and we look at these kind of solutions. So our result is the following. So this result applies also to inequalities, not just to equalities. So it says that, so if Q is sum of these weights and lambda is less than this Fujita exponent, and if U is larger than U to the power alpha, so for example, you can take f of U to be equal to U to the power alpha if you want to have this exactly Fujita case, then even inequality doesn't have solutions, so there is always blow. So if alpha is smaller than this number, then there is blow up. If alpha is equal to this number, then there is also blow up, but now for the equation, and if alpha is larger than this number, then there are global solutions. Okay, so this is the situation. I would say also complete understanding of Fujita effect for general Hermande for general Hermande vector fields. So this is without group structure now. Okay, so and problem 3, I think I have some minutes left. Problem 3 is concave case, and here we can prove surprisingly very general results about underlying space. We don't need it to be a Rn, we don't need it to be a group. What is surprising, we just need it to be a measure space, only measure space. So X is a measure space. We consider this equation. Okay, you may ask, if we have a measure space, what is this L? So we go around it. We say the following, that we assume that operator L has a kernel, integral kernel K, and instead of this equation, we look at this equation in the integral formulation. Namely, we look at this equation. So in this way, we bypass necessity immediately. So we extend generality because we don't have to talk about operator L. We talk about solution to this equation in the integral form like this. When K, we keep in mind that K is the integral kernel of L. So such equations, they are known as, and also here, I would say that it's a more general situation. We have this forcing term depending on T and X, and here we have a function H. Before was depending only on T. Now it can depend on T and X. So if nonlinearity is concave, it's nice in the sense that it allows us to obtain results in much more general situation. So in the literature, these are called Hammerstein-Volterra type integral equation, and on the kernel, we will not make much assumptions. We just assume that it's measurable, positive, like we have it for cases of Laplacian and sub-Laplacian, so it's just measurable, positive, and when we look at this integral, then it has these estimates, and basically there are two cases. If lambdas are equal to 0, then the integral is, for example, equal to 1, like we have in the cases of Rn, for example, or the previous cases, integral of the heat kernel is equal to 1. So this is called stochastic case. And another situation when there is exponential decay, so lambda minus lambda plus are positive, we call it substochastic case. So this is the case if operator L has a spectral gap, for example. So if spectral starts from 0, then we have stochastic case, but spectral gap, if we are, for example, in symmetric spaces, or we add some potential operator to L, or we like hyperbolic space, for example, then there is spectral gap, then we'll have this exponential decay. So there are these two cases. We will have results for both cases, but in substochastic case, we can prove more general results. We can drop some assumptions because we have additional exponential decay. So what settings it covers? So we can where it applies to, and these are all new results, I believe. Consequences of our result, most of them are new. So, for example, L is Laplace-Beltrami operator on complete remaining manifold with bounded from below Ricci curvature. This is one case when our results apply. Another remaining manifolds without curvature condition, but with volume growth, which is quite exponential to R squared. So we can allow very fast exponential growth. This will cover this case. For example, all symmetric spaces covered by this situation. We can consider sum of squares on general groups covered by this situation. We can consider sublaplacians before was remaining manifold, but on subremaining manifold. Consider sublaplacians satisfying some so-called curvature dimension inequalities. I will not go into this, but it is this case and a bit of another abstract condition for when this holds, but I don't have time to talk about it. So this is assumptions that we have. So nonlinearity G. So G is nonlinearity. H is function in front of it, but nonlinearity, what we assume, again, very mild assumption. G of 0 is 0, and it's so increasing concave function. This is a technical condition about G. Sometimes we can drop it. For example, if G is strongly concave under these assumptions, and under these conditions, that this assumption is automatically satisfied. So examples are, as I said before, u to the power alpha, where alpha between 0 and 1. Also this kind of nonlinearities, so they are all concave or strongly concave. So the function G, which is a condition, which you may think here is a, no, there is no G here, but G here, which is u of 0. So this is basically the initial condition. U of 0 is G of 0. But here is more general because we allow G of depending on xt. For the Cauchy problem, it would be just would be just Cauchy data. So we assume it's non-negative, and sometimes we assume this that it's bounded away from 0. But sometimes I will indicate that we don't need to assume it always. And so G is non-negative bounded function, and H, the function in front of G, it is just a measurable function, non-negative measurable function. So very general assumptions, and this is our theorem with colleagues, Gira Evtesyan, who was in Ghent University for a while, and then Khachaturian in Armenia. We have the following result, that if we assume that this H, this is a function in front of the Laplacian, is bounded by some functions of t. So it covers the case when it is just a function of t, but we can allow depending on x also. Then the result is the following, that there is no Fujita exponent in this case. there is always global existence. So there is always, there exists always global bounded solution of that equation. And remember that in when we I didn't mention it, but when we talk about global existence for Fujita exponent, we talk only about small data, global existence for small data. So here we have global existence for any data, also for large data. Then we don't have blow up, we always have global existence for large data. Moreover, we can do a bit more. We can, and you can see partly idea of the proof from this formulation is that we can have these iterations, iteration scheme coming from integral equation, and the point is that these iterative approximations, they converge, they give us a decreasing sequence which converges to our solution. So this is existence, uniqueness. We have always uniqueness of solution. And as I said, sometimes we assume that G is bounded away from zero. Then if they're bounded away from zero, then we can also get the rate of convergence of this scheme, of these approximations. But if you don't assume these conditions, then we just have convergence without the rate. Okay, so this is a rather general result. And I think my time is finishing. So let me summarize. So in this talk, so what we did, we established when we have time-dependent nonlinearity, then we establish necessary conditions on generally modularly groups, or necessary conditions for blow-up, which is equivalent to sufficient conditions for the existence of solutions. In the case of Heisenberg group, we obtained implication in the other direction, and they coincide in particular cases, but in general, they up to now, according to this result, they didn't coincide. And so heat equations for general Fibonacci sum of squares without group structure. I presented Fujita exponent, so this problem is resolved. I would say we have formula for the Fujita exponent. We can obtain different implications for this. We can also, so this was nonlinearities I consider convex, like power type, but we can consider also logarithmic type. I didn't talk about this here. And finally, for concave nonlinearities, we have global existence and uniqueness, not just for small data, for large data, and without any Fujita threshold, because nonlinearity power in this case is less than 1. So we always have global existence. And I think I stop here. Thank you.
Okay, thank you. Thank you, Professor Michael, for your nice and interesting talk. Okay, so I think now we have time for questions. So let me check the chat on YouTube. If someone has question, you can write on the chat. Please remember that. Okay, I am checking. Okay. Looks like there are no questions for now. Maybe Jenny or the Professor Jenny has a question, or the Professor Christiana. Please, you can raise your virtual hand also. Okay. Okay, Jenny Jenny said, no thanks, everything is clear.
Thank you. Thank you. I'm glad. Yes.
Yeah, was very clear.
Maybe everything is clear. So yes, and
Yeah.
of
On
course
the
no.
chat, okay, Jenny, thank you very much for the nice presentation. Yes.
You're welcome.
Okay, on the chat, we have hello from Italy. Okay, so we are people from Italy at this moment. Okay, we have a question. What results do you have if F is not continuous? Juan Pablo Lopez.
Yeah. Yeah, if f is not continuous, then we don't have results. But no, okay, depends. If concave case, we have these results, which so here in the concave case, we don't assume continuity. So if we're in the concave, no, sorry, we assume continuity. So yeah, we assume continuity indeed, and in the previous cases we assume continuity. Then we don't have results for if f is not continuous. Yeah, we don't have results. We haven't looked at it, but maybe this year, maybe it can bring some effects. That's right. But we don't have results.
Okay, thank you. Julio Delgado tell us, thank you so much. Thank you so much. Very nice talk, Julio Delgado. Okay, so I think.
Okay, thank you.
Thank you, Professor, again.
Yes.
Okay, so for now, we have a few minutes to the next talk. The next talk will start in 4 minutes. Okay, so I think we will wait. Our next speaker is the Professor Cristiana de Phillips.
Hello?
Professor, okay, you're here. Great.
Yeah. Hi, Cristiana.
Okay.
Hello. Should
Hello,
I share the slides?
Yeah, you can try.
Yeah, no, because in general it takes me a few minutes to do this. So
Also, you have a few
I'm
minutes,
not very
don't worry.
good with this. Okay, let's do like this. Come on, last time it worked. Window. Do you see it? Okay. No. Do you see them now?
No?
Okay. Okay, so probably. Okay, so maybe it can make sense to do the following. Give me 1 second. Okay. Chrome tab. For some reason, it doesn't allow me to share my slide. Okay, let's try this. Works?
It seems, yes.
Okay, so let me just rename it. Okay, fantastic. Is the visual clean or?
Yes, it's not full screen perhaps, but it's clear.
Let me try if because I have them full screen on my computer, but Do you know how to share slides differently? I only know this
Control L, perhaps?
one. Control L?
No.
No, nothing happens. Window. Yeah, sorry. Window. No. Then it goes like this. I guess it is the easiest way.
So we can read. Presentation mode, Cristiana?
Eccolo, very good.
Presentation.
Fantastic.
Okay.
Great, you spotted it. Thank you a lot.
Okay, so perhaps we can start. So it's my pleasure to introduce Cristiana. Cristiana De Filippis is an Italian mathematician whose research focuses on regularity theory for elliptic and parabolic partial differential equations. She completed her PhD at the University of Oxford in 2020 under the supervision of Christensen. After a postdoc position at the University of Turin, she joined the University of Parma as an assistant professor in 2021, and now she is a full professor in the same university. Cristiana has received numerous prestigious distinctions recognizing her outstanding contributions to the analysis of partial differential equations. Among these are the ICMAM Early Career Prize in Analysis of Partial Differential Equations in 2025, then the European Mathematical Society Prize 2024, the Bardozzi Prize 2023, the Gioacchino Iapicchino Prize awarded by the Accademia Nazionale dei Licei in 2020, while in 2023 she was elected as an inaugural fellow of the European Mathematical Society Young Academy. In addition to these honors, she has obtained important competitive research fundings, including a prestigious European Research Council starting grant awarded in 2025. Another recognition of the originality and international impact of her research. Today, she will speak on non-uniform ellipticity and nonlinear potential. Please, Cristiana, and thanks for your talk.
So thank you a lot for the very generous introduction, and my apologies for the usual technical problems. Thanks also to the organizer for allowing me to present my results in such a prestigious venue. Okay, I'm going to report some recent regularity results on mu elliptic problems. Okay, what am I talking about? Okay, sorry. What's wrong with this? Okay. This, why it doesn't stop? Okay. Fantastic. Okay, so what is mu ellipticity? Keep in mind as a key model example the non-parametric area integral, okay? More generally, mu ellipticity is a very degenerate ellipticity type that features this configuration, okay? So you are essentially trapping the action of, say, regular autonomous integrand between, in the large, two negative powers of the gradient variable. Indeed, here mu is larger or equal than 1, and G is a possibly non-decreasing function. Okay? Okay, now, why the regularity theory for this class of problems is pretty delicate. First of all, because they are intrinsically non-uniformly elliptic. Indeed, if you try to quantify the ratio between the highest and the lowest eigenvalue of the Hessian of a mu-elliptic integrand, that is the ellipticity ratio related to this problem, you see that it immediately blows up on large values of the gradient variable, just because your problem is mu-elliptic. You do not need to quantify the size of mu or whatever, okay? And whenever you're dealing with this class of equations or functionals, well, the very first fundamental step you want to make in order to secure regularity is proving gradient boundedness. That is Lipschitz regularity for solutions. This is already noted by Giaquinta and Giusti, using as a test bed precisely the minimal surface equation. Indeed, as soon as you know that the gradient of solutions is bounded, then this object becomes uniformly elliptic, quadratic, and you can push the regularity as much as you want. So, if all of us agree on the fact that the most important aspect for regularity is being able to show that solutions are Lipschitz continuous, then you understand where the difficulty in dealing with mu-elliptic problems also relies. Indeed, remember that that you are controlling negative powers of the gradient variable, meaning that mu-ellipticity plays against the achievement of Lipschitz regularity. Indeed, the largest the gradient variable becomes, the smallest is the amount of information that you control. You lose more and more information. That's why these type of equations are very, very delicate under the point of view of regularity. Now, a natural question would be if mu-elliptic problems, or more generally, non-uniform elliptic problems, live in maths textbook, or they have something to do with reality. Well, they're actually pretty much motivated, but by the modeling of real objects, for instance, electrorheological fluids, or strongly anisotropic materials like lava, tissues, probably your breakfast, like milk and cereals, or mud as well, or a mixture of fluids with different hardening properties. Then we already mentioned minimal surfaces. There are also important models in electromagnetism, and they also appear in weak KEM theory. Let me be more specific under this point of view. Indeed, the non-parametric area integral is mu-elliptic with degree of mu-ellipticity equal to 3. Okay, and the very same model can be generalized up to some extent by considering, let's say, variation on the non-parametric area integrand as well. Or we can look at the Lorentzian brother of the non-parametric area integral, that is the electrostatic Born field energy. All of these are non-uniformly elliptic. But we could also consider L-log-L type models, whose most prominent example is this one. They play important roles, for instance, in material science, in the modeling of Prandtl layering fluids, or one can compose more and more logarithms in order to approach linear growth, but still remaining quantitatively superlinear. Okay, so all of these examples are mu-elliptic and therefore non-uniformly elliptic. Okay, now the matter of regularity in non-uniformly elliptic problems, I hope I convinced you that it is a rather difficult task. Indeed, it attracted the attention of lots of important names in mathematics before the 70s, where very heavy machineries such as global methods, barriers, classical solutions, strong solutions were employed. But let's say that significant progress appeared after the 80s, in particular, thanks to the work of Chekhov, who introduced a series of very specific models that are, if you want, closer to the uniformly elliptic world rather than the non-uniformly elliptic one, but give you lots of insights towards the general theory. Moreover, Cellini and Marcellini laid the foundation for the model, the modern variational approach. It is the one that nowadays everybody uses and therefore allowed to overcome the use of global methods, classical or strong solutions. Okay, so essentially the possibility of working in a variational setting allows us to work, okay, precisely where you can prove existence of solutions. And finally, Esposito, Leonetti, and Mingione connected the regularity of solutions to non-uniformly elliptic problems to a classical phenomenon in the calculus of variations, that is the occurrence of Lagrangian phenomenon. And as we shall see, the two things are pretty much linked together. Okay, what about the basics of regularity in mu-elliptic problems? If we focus, for instance, on this basic model example, the joint efforts of Bombieri, De Giorgi, Miranda, Ladichanskaya, and Duraltseva, Trudinger, Leon, Simon, and more recently Beck and Schmidt, that push even further the regularity for this class of autonomous integrals, tells us that if mu stay between 1 and 3, 3, remember, is the case of minimal surfaces, so it corresponds to p equal 2, then solutions have continuous gradient, and then you can push it even further if you like. Keep in mind that this limitation, okay, mu less than or equal than 3, is essentially telling you that the ellipticity ratio related to this class of problems cannot blow up too fast, okay? In particular, if mu is larger than 3, then nothing is known, nor on the regularity side, nor on the irregularity side. So it is open, okay? Still. Of course, the matter of mu ellipticity can be made even more wild by considering also an isotropic term that forces a Q growth from above and reflects on the growth ellipticity feature of the integrand itself by leading to mu Q ellipticity. Okay, so you have an even wilder behavior of the action of your integrand from above. Okay, what about the regularity for this class of mu elliptic problems? Well, first result is due to Fuchs and Mingione, that again prove that if Q is not too large, meaning if the ellipticity ratio doesn't blow up too fast, then solutions have continuous gradient, and of course the result can be generalized to the vectorial situation, of course, provided that the integrands depend on the modulus of the gradient. They can cover the case of iterated logarithms, as well as obstacle problems, of course, for the scalar setting. Bildauer and Fuchs later on achieved partial regularity within this setting, and let's say that the restriction on the blow-up rate of the ellipticity ratio was recently improved by Beck, Gemeneider, and Schaffner. Okay. What about bounded solutions, bounded minima? We already saw with the Bombieri, De Giorgi, Miranda, and Ladichanskaya and Duraltseva that boundedness played a rather consistent role in achieving regularity already in the minimal surface case. What can be said about mu Q ellipticity? Well, that bounded minima enlarges, if not maximizes, the non-uniformity range. And this is a result of Bildauer and Fuchs. However, all the results that I presented so far strongly rely on the possibility of differentiating twice your variational integral. One is your Euler-Lagrange equation that is satisfied by minimizers. And the second time, you need to totally differentiate your Euler-Lagrange equation. And then, if you're considering bounded minima, then you need to combine this with Gagliardoni-Rebec type inequalities, okay? In order to construct an unbalanced Moser iteration on a Marcellini. This perfectly works if your integrand allows you to differentiate. But this is in general not the case. Indeed, if you plug in, for instance, non-differentiable ingredients, you can no longer walk this path. Okay, and so all this construction delivered up to now simply breaks down. Okay. Another important message that the regularity results achieved so far tell you are that not all the values of mu and q are admissible, or not all of them guarantee regularity. Meaning that in all these examples, in all these results that I told you, the ellipticity ratio cannot blow up too fast. And this is a common feature of non-uniformly elliptic problems. Indeed, if we look at polynomial non-uniformity that can be, in a sense, quantified by trapping the action of your integrand between two different powers of the gradient variable, in this case, the situation was clarified around the end of the 80s. Indeed, Giaquinta and Marcellini and Dong proved that a suitable constraint on the blow-up rate of the ellipticity ratio is necessary and sufficient condition for regularity. In particular, if the ellipticity ratio blows up, then unbounded minimizers might appear. What does it mean? Well, this is a rather striking phenomenon typical of non-uniform elliptic problems. Indeed, this happened for strongly convex integrand in the scalar setting. This is again a peculiarity of non-uniformly elliptic variational integrals. Indeed, if you want to see within the same setting irregularity in the uniformly elliptic setting, then you want to look at vectorial problems in order to experience formation of singularities. And so what about non-autonomous integrals? So what happens if we plug in ingredients? Well, this is a rather delicate phenomenology because if you already think to the case of harmonic maps, right? They are smooth. It is a Weyl lemma. Because up to a certain scale, you can essentially swap your function with a modification bit. However, as soon as I plug in ingredients, let's say Elder continuous ingredients, then the presence of these external components somehow inhibits the self-improving properties of the Laplacian, and therefore you can only prove Elder continuity of the gradient, for instance. This is a classical Schauder theory. Therefore, if we plug in ingredients in non-uniformly elliptic problems, then the situation becomes pretty much worse. And in particular, novel phenomenologies and novel interactions between coefficient and gradient variable might occur. As a test bed, let's consider this model introduced by Zhikov in the setting of homogenization and for studying the possible occurrence of Lavrentiev phenomenon. Now, the structure is pretty simple. You have a P Laplacian plus non-negative weight Q Laplacian, and what should we expect under the point of view of regularity? Well, point by point, this object is uniformly elliptic. Indeed, if A were constant, then either if it is positive or zero, doesn't matter. Minimizers have always solved their continuous gradient. So one expects that if A is allowed to vary, so it is non-negative, let's assume that this is Elder continuous, then if it is Elder continuous, I expect Elder continuous gradient, okay? And this is sharp, thanks to a counterexample due to Ralseva that tells you that in possibly degenerate integrals, like the P Laplacian, the best you can get is gradient Elder continuity. So the picture is rather clear. However, the fact that A is allowed to vanish gives to this model a very mild amount of non-uniformity that still allows to escape the classical setting. Indeed, assume for the moment that A is just bounded. And let's imagine that we are on this checkerboard. We flip a coin and decide if we want to go left or right, so we go either blue or red. Let's say that A is 1 on the red zone and 0 on the blue zone. So we can switch on and off, depending on where we decide to go, the LQ ellipticity information. But this is a very violent interaction that goes beyond the classical, perturbative behavior of coefficients allowed by uniform ellipticity. Non-uniform ellipticity allows for this. And indeed, this new coefficient solutions interaction gives rise to very huge irregularity phenomena. Indeed, this is a counterexample due to Fonseca, Mali, and Mingione that proved that, again, if the ellipticity ratio blows up too fast, and this is quantified by these inequalities linking ambient dimension, growth ellipticity exponents P and Q, and alpha Elder exponent, then one can construct a family of Dirichlet problems driven by this double phase operator, such that solutions have set of essential discontinuity points of nearly maximal Hausdorff dimension, meaning that solutions are not even better than any of their competitors, okay? But why this is significant? Again, this is a scalar example. Remember the peculiarity of non-uniform ellipticity already in the autonomous setting. You might see irregular solutions, even when in the uniform elliptic case, regularity should be expected. Moreover, this example holds for minima, so you are not violating any energetic information. The boundary datum is Lipschitz continuous, it can be taken even smooth, no problems. The Dirichlet problem is defined on a ball, so there is no weird formation of singularities coming from cusps on the domain. The integrand is radial, so there is no huge anisotropy of any kind. It can be made non-degenerate or non-singular. So now we killed essentially any type of, any possible source of singularities. Therefore, the real origin of singularity is the harsh interaction between coefficient and gradient variable. And I will turn back on this. Indeed, this result was later on sharpened by Balchi, Dinning, and Surnashov that showed that actually the set of essential discontinuity points of minima, as soon as Q is too large, as soon as the ellipticity ratio blows up too fast, then the set of essential discontinuity points of solutions might have maximal Hausdorff dimension, that is n minus p. Moreover, the Lavrentiev phenomenon might occur in the Dirichlet class defined upon smooth boundary data. The density of smooth maps in modular convergence might fail, while regularity holds whenever Q is less than or equal than P plus alpha, okay? Okay, moving further, we just spotted a classical fact for uniformly elliptic problems that is Schauder theory. If coefficients are elder, then the gradient is correspondingly elder. And an open problem immediately emerges that tells you that what happens in the non-uniformly elliptic setting? Does Schauder theory hold? And we already saw that several of the paradigm of classical Schauder theory might break down as soon as a very little amount of non-uniformity appears, as it is the case of the double phase energy, okay? Indeed, this was a problem raised at several stages in the literature. Here, indeed, we see a comment of Lieberman under a classical paper of Giaquinta and Giusti. Indeed, Lieberman said that the perturbative approach of Giaquinta and Giusti perfectly works in the uniformly elliptic setting, but dramatically fails in the non-uniformly elliptic one unless they don't already start with Lipschitz regular solutions, but this essentially kills non-uniformity, okay? I mean, if the gradient is not allowed to blow up, then, I mean, non-uniformity simply doesn't make any sense. Moreover, another classical theorem due to Ladizhenskaya and Duraltseva shows you several limitations of the previous methodology for delivering Schauder theory in the non-uniformly elliptic setting. Indeed, they had to assume bounded gradients. And moreover, all the entries of the nonlinear field driving the equation are supposed to be differentiable. But remember, in the light of Uraltseva's counterexample, as non-uniformly elliptic models include possibly degenerate models, then the best regularity you could expect is a gradient intercontinuity. Therefore, it doesn't make any sense to consider ingredients that are more regular than just elder, okay? And in particular, Ivanov identified where is the chief difficulty in dealing with this type of results. That was achieving Lipschitz bounds. That was the key problem, okay? Because the perturbative methods were no longer functioning. Indeed, once Lipschitz continuity is there, then non-uniformity becomes immaterial, and one can trace the problem back to the realm of uniformly elliptic problems, okay? Moreover, when mu ellipticity comes into play, there is a further difficulty, that is the problematic compatibility of mu ellipticity with the classical Schauder setting that prescribe elder continuous ingredients. And this will be addressed. Indeed, an answer to this issue can be found in these papers. And I mean, in this talk, I will try to focus on the matter of the validity of Schauder theory in the mu elliptic setting, and in particular on the compatibility of mu elliptic problems with elder ingredients. Okay, so one of the main novelties of our approach was indeed the achievement of direct Lipschitz estimates. Okay, we prove Lipschitz estimates in a direct way. So indeed, Ivanov was right. This is the main difficulty to overcome. However, in order to do this, we had to overcome a 100-year-old paradigm for the achievement of Lipschitz estimates in non-differentiable problems. Indeed, if you think to, I don't know, basic uniformly elliptic PDEs with elder ingredients, how do you prove Lipschitz regularity? Well, you first prove that the gradient is elder continuous, and then you retain gradient boundedness. This is the usual way. However, this is no longer feasible in the non-uniformly elliptic setting, owing to the deep non-homogeneity of all the excess decay estimates involved. And therefore, one needs to first go to Lipschitz and then try to prove continuity or elder continuity of the gradient. So let's have a look to what happened in the classical literature for mu elliptic problems. Well, in all the results you can find, coefficients are always assumed to be C2 regular. And this might ring some bell. Indeed, the classical counterexamples due to Giaquinta, Modica, and Sujak tells you that if the ellipticity ratio blows up too fast, okay, then one can construct a very simple model integron with the C2 regular coefficients, even smooth, such that minimizer fail to belong to W11. And this is particularly problematic, okay? And even if you want more disturbing phenomenology, appears in the classical area setting. Also in this case, if coefficient fail to be C2, then minima might fail to belong to W11, okay? So you might find minima that just belong to BV. And these two counterexamples highlight how problematic is mu ellipticity with respect to Schauder theory. So maybe two objects with that might be difficult to put them together, okay? Okay, so let's try to see what happens for the regularity of non-autonomous mu elliptic problems. Can we salvage Schauder theory somehow? I will try to convince you that for at least a reasonably large class of mu elliptic problems, Schauder theory is there in an optimal fashion, okay? So let's have a look to the case of logarithmic type energies. Those nearly linear growth, meaning that they are superlinear at infinity in this sense, but grow slower than any power larger than 1. This is a sort of limiting configuration before the classical area case, okay? Our first typical model example is the L-log-L energy that was deeply studied by Frese, Fuchs, and Seregin. Is rather common indeed in harmonic analysis. We see that it is uniformly elliptic with a logarithmic type of blow-up of the ellipticity ratio. So, classical methods fail it is non-uniformly elliptic indeed, and the same can be said about iterated logarithms. in which mu ellipticity appears again and the ellipticity ratio again blows up even faster. What do we have here? Under the point of view of Schauder theory, for L-log-L type energy, this was settled by myself and Mingione, and later on sharpened by myself, Filomena De Filippis, and Mirko Piccinini. What we have here is that if U is a local minimizer of this L-log-L energy with a coefficient C that stays away from 1, and it is beta continuous, then the classical Schauder implication holds. And of course, similar gradient Elder continuity holds if we consider iterated logarithms. And of course, this result can be reasonably extended to the vectorial situation, provided that functional satisfy so-called Uhlenbeck structure, meaning that they depend on the modulus of the gradient. So what about the case of the double phase energy? So let's try to understand what's going on in this limiting configuration, and if this can, give some type of explanation about what happens for Schauder theory when some anisotropicity is there, okay? And in particular, what is the relation between mu ellipticity and Elder continuity? Okay, so let's consider this model with, of course, iterated logarithmic variant. This is, of course, non-uniformly elliptic, therefore any type of perturbative approach immediately fails this situation. And let's see what we have here. Well, if we take local minimizers of this energy and we impose that the ellipticity ratio doesn't blow up too fast, then we can conclude that the gradient is locally Elder continuous in omega. This essentially parallels the classical result when polynomial non-uniform ellipticity appears in a quantitatively superlinear setting. And the same bunch of techniques can be extended to cover various type of logarithmic growing models. But let's have a deeper look at the literature, and let's see what happens if we consider bounded minima, bounded solutions. Okay. Indeed, looking back at the past literature, we see that the combination of local boundedness with a suitable constraint on the blow-up of the ellipticity ratio leads to sharp result. This is indeed the case. What we have for the basic, for this very basic model is that we take bounded minimum. A here is Elder continuous. We assume that Q is less than 1 plus alpha, and then the gradient is locally Elder continuous in omega. I want to try to convince you that this is sharp, okay? And in particular, this is the right setting where to study Schauder theory mu elliptic problems. Of course, the one that I showed you is a model result, a model case of a more general results that allow to consider iterated logarithms as well as obstacle problems. So, under classical assumption on the obstacle, what we obtain is that if Q is little less than 1 plus alpha and solutions are bounded, then the gradient of minima is Elder continuous. And in particular, if we are dealing with non-singular problems, meaning that here S is strictly positive, then we can recover, at least in the plain logarithmic case, we can recover alpha Elder continuity for the gradient. Well, if mu is larger than 1, then we have a loss of alpha over 2. Still, what are the main difficulties in dealing with this problem? Well, the main difficulty is covering the whole non-uniformity range. How we do this? Well, the basic observation is that the integrand is non-differentiable. So in particular, there are no ways to achieve a second variation. However, if we read the Elder continuity as fractional differentiability, we can observe that the integrand possesses like 1 plus alpha derivative, almost. And therefore, one can start thinking to build up a fractional Moser iteration to get regularity. However, mu ellipticity hits harder also under this point of view. Indeed, the fact that you are dealing with mu elliptic problems forces a loss of differentiability gain that results in a loss of alpha over 2 in the non-uniformity range. Okay, therefore one needs to bypass also this obstruction. The way to do this is to construct a hybrid reverse-Elder inequality that interpolates between any arbitrarily high Lebesgue norm of the gradient. Here T can be anything between 1 and infinity, of course, infinity excluded, and the L1 norm of the gradient itself. However, this constant must be proportional to an arbitrarily small power of the L infinity norm of the gradient. And what is most important is that this omega is as small as we like, but it does not depend on T. So at this stage, one can say, well, then you are done, right? Because you just send T to plus infinity and you have your Lipschitz control. And then you can reabsorb the small L infinity norm that you have on the right. This is not the case because fractional Moser type iterations are linear iteration, and therefore you have a linear gain in integrability that cannot be killed by sending just by sending T to plus infinity. Therefore, what we control is any arbitrarily high Lebesgue norm of the gradient via an arbitrarily small L infinity norm of the gradient, arbitrarily small power of the L infinity norm of the gradient. And this will be particularly helpful when plugging in this kind of information in a nonlinear potential theoretic version of the George's iteration that will eventually result in Lipschitz regularity subject to the sharpest non-uniformity threshold. Now, other technical novelties that appear in this paper is a novel approach to variational obstacle problems that bypasses classical techniques that dates back to the 80s. Okay. Indeed, how do you deal with variational obstacle problems? Well, the first approach is linearization. After Duzar and Fuchs, indeed, one can show that minima of variational obstacle problems of this type, and keep in mind that the presence of an obstacle is actually a convex constraint. Therefore, minima of this class of problems are actually unconstrained local minimizers of the same variational integrals with a forcing term, which is not problematic, but we should see how the forcing term looks like. Now, the forcing term essentially behaves as the divergence of the f of x ellipsi, which perfectly makes sense whenever this object is differentiable, okay? Which is the case if f is suitably, of course, suitably differentiable in the gradient variable and coefficient that represent a major obstruction. If the coefficient is merely Hilder, this object does not make any sense, and there is no way around this. Another approach is the perturbative one after Coe, and the idea is essentially to compare your minimum of the obstacle problem with a forced Dirichlet problem of this form. So you are again moving the obstacle from a pointwise constraint to a right-hand side, and then you compare this forced variational integral to an homogeneous one in order to extract regularity from the frozen problem. However, here there is an even major obstruction that is represented by the perturbative approach that, remember, strongly require uniform ellipticity. Okay? If that thing breaks down, there are no ways to adapt this type of approach for the non-uniformly elliptic setting. So both these techniques fails already for our basic model. Indeed, linearization fails because if A is Elder continuous, okay, this quantity is meaningless. Again, perturbation fails because our model is mu-elliptic, that is non-uniformly elliptic. And so you no longer have homogeneous excess decay estimates. And what we do is instead, again, a hybrid approach that allows to fractionally differentiate the problem and then bypass all this major obstruction created by the coexistence of non-differentiable ingredients and mu-ellipticity. Now, I insisted a lot about the fact that our result is sharp, in the sense that if the ellipticity ratio blows up faster than the one that I showed you, then serious irregularity phenomena might appear. Let me show you why. Well, let's assume that we are in dimension n larger or equal than 2. Let me consider a cube, the n-dimensional cube, and let me assume that Q is larger than 1 plus alpha. As this image suggests, counter-type fractals will play a major role in this situation. Okay, so what do we have? Well, first of all, we can construct a modulating coefficient A that is alpha Elder continuous, a smooth boundary datum, and force Lavrentiev phenomenon to occur in the Dirichlet class with boundary datum equal to U0. Indeed, we can show that the infimum attained by our log double phase energy in U0 plus W11 of Q is strictly smaller than the infimum attained by the same functional on the set of smooth of C infinity with compactly support functions and U0 trace on the boundary. This is the classical formulation of Lavrentiev phenomenon. Moreover, we can simultaneously show that the density of smooth maps with respect to modular convergent fails. And so we already saw that as soon as the ellipticity ratio blows up, even basic functional analytic properties or spaces of function defined by the finiteness of this energy might immediately break down. But what is more significant to me is the lack of regularity. Indeed, what we can show is that give me any epsilon, I can construct modulating enough Elder continuous modulating coefficient and a smooth boundary datum such that the solutions to this Dirichlet problem fails to belong to W1P for all P larger than 1 plus epsilon. Meaning that, of course, in this situation, Schauder theory instantaneously fails. I mean, your solution does not belong to W12, for instance, if you take epsilon sufficiently small. And so in particular, it cannot belong to W1 infinity, it cannot be, the gradient cannot be continuous. Okay, how do we prove this result? Well, this is essentially a story of a malicious competitor that is admitted in the class of competitors for this Dirichlet problem by a cheating coefficient, and a poor honest boundary datum that proved to be completely helpless in this situation. Now, aside from jokes, what is the idea here? Well, the idea is that the fact that A is allowed to vanish, okay, permit to certain irregular maps that in principle do not have finite W1Q energy to enter within the finite energy class for this functional. Because you can essentially force A to vanish whenever the gradient of this competitor is non-zero. This way, you are forcing your competitor to have finite energy, and therefore to be admissible for your problem. So how do you construct it? Essentially, you take the regularized version of characteristic functions of double cones with tips on a very dense counterfractal, okay? Then, which is compactly contained inside your unitary cube. Once you have used your very bad competitor, then you cut it off, smooth it out, and you can make it compatible with a very regular trace at the boundary of the cube. Then the idea is to prescribe very high traces at two parallel faces of the cube with different sign. So this is more or less the picture. And if you overlap those two images, you see that A precisely hides those regions in which the competitor oscillates very widely. Okay? Okay. Then how do we conclude? Well, the fact that you have on parallel faces very high traces with different sign, with opposite sign, okay, force the minimum to have too high energy to, cover this job. And therefore, it is forced to strongly oscillate on the fractal. This way, one can, in some sense, force the set of essential discontinuity points of view inside the fractal in such a way that the Hausdorff dimension of it becomes larger or equal than n minus 1 minus epsilon, okay? But then basic Sobolev theory kicks in and tells you that since the set of your set of essential discontinuity points is so large, is so big, you cannot belong to W1P for all P larger than 1 plus epsilon, okay? Otherwise, this object would have Hausdorff dimension strictly below n minus 1 minus epsilon. And this leads to a contradiction, okay? What about general mu-elliptic problems? So how do they react to the presence of Elder coefficient? In particular, can we make mu-ellipticity compatible with Schauder theory? Well, what we prove is that the same constructions for the counterexample works for a suitable relaxation of this area type integral, okay? So there are no hopes of regularity whatsoever as soon as Q is larger than 1 plus alpha. Now, within this threshold, where again you can show that minima will never be Lipschitz continuous in particular, provided that this holds. And what you can see from this threshold, and in particular what you say, and indeed, if we have a look at the various bunch of techniques that are employed in order to show regularity, the Q anisotropy should be balanced within this way, okay? Which means, in our situation, recalling that mu is equal to p plus 1, it means that an inequality of this type should hold, okay? But what's the problem here? Well, the problem is that p is larger than 1, right? Therefore, in order to be able to deal with any alpha Elder continuous coefficients, also with coefficients that have a very low Elder continuity exponent, then you have to take mu very close to 1, meaning that a compatible configuration with Schauder theory is the mu ellipticity given by L log L type models, okay, as our double phase one. Okay, so this is those are the papers that are the main references for this work. And I thank you for the attention and apologize again for the technical inconvenience.
So thank you very much, Christiana, for your nice and clear presentation. Are there some questions or comments? You can write in the chat. For the moment, there is nothing. I have just a curiosity, Christiana.
Please.
So you assume that the function a is greater positive, okay? So it can be also 0. But
Yeah.
does the region where a vanish need to satisfy any particular geometric properties, or can be nothing?
No, it can be whatever you want. And this is one of the chief difficulties in dealing with this class of integrals. The fact that you have essentially zero control on the zero level set of A. You only know that A, if you are after regularity, A is an Elder continuous function, and you have the zero set of an alpha Elder continuous function, which is what it is. You have no additional information. And you actually achieve regularity without having any information on this.
Okay, so it can be also 0 at the boundary of omega. Or
It is free to do whatever you want. It is
okay.
just an Elder continuous function that can vanish wherever it prefers.
Okay, thank you very much. I don't know
Thanks
if
to you.
there are other questions. If not, I thank you again, Christiana. Thank you very much,
Thanks to
Christiana,
you.
for your contribution, your talk.
Thanks a lot. Let me
Thank you very
stop
much. So
sharing.
we have perhaps about 10 minutes before the other talk. So we can make a break of 8 minutes.
Hello, Jenny.
Hi, Andrea. I
Yes.
don't know if the next speaker is
It's not
already.
here yet, but it's just 10 minutes
Yeah, so
before, so we will just wait for her and we will connect everything later.
we have 9 minutes. So
Yes,
we can make
now
just
9. Yeah.
a short break. Okay.
Thank you.
No, thank you.
Hello, Professor Sylvie. Hello, Professor Silvi, can you hear us?
Thank you.
Hola, profesora. Ya
Hola,
te...
¿cómo está? ¿Cómo
Bien, bien,
está?
¿y tú?
Pongo la video.
Eh,
Sí,
si tú quieres, porque ya vi el correo. Sí,
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 estoy con un dolor de cabeza tremendo, pero voy a intentar, voy a hacer lo que pueda.
si tú
Sí,
quieres,
sí,
puedes
sí, sí.
remover el video y te
Gracias. No,
escuchamos
no,
solamente.
no, está bien, yo creo que es
Ok,
mejor por video.
ok. Gracias, profe.
No, no tenemos tiempo de hablar, pero otro día.
Otro día te escribiré un correo y hablamos
Y
mejor.
dándome noticias, me gustaría.
Sí, 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 sí.
Gracias. Después de la charla, pues después del evento, quizá.
Sí, sí,
Muchas
profe,
gracias.
claro. Claro, yo te envío un correo. Bueno, qué pesar que estés así enfermita hoy. Muchas gracias, de verdad.
No es hoy, es que no, es hace varios días, pero
Ah, sí,
y-
sí.
sí, vamos a ver, vamos a ver. ¿Cuándo empiezo? Pronto, ¿no?
Sí, profe, en 4 días. Es que en cuatro, sorry. En cuatro
Gracias,
minutos.
eso sería muy bien.
En 4 minutos. En 4 minutos.
Ok.
Si quieres,
Eh,
podemos compartir la pantalla
sí, sí, verdad.
y vamos cuadrando todo. Dale.
Espera que eh, vea si es este.
Sí, la veo.
Sí, pero no creo que sea el correcto. Espera. Eh, eh, Espera, me toca mirar todo lo que tengo abierto porque Freigabe stoppen, un momento, un minuto. Eh, que tengo abierto aquí. Ah, no, es este, entonces debe ser lo que abrí. Eh, freigeben, freigeben. Ok, sí, parece ser este. Eh, ¿Lo ves?
Sí, profe, sí lo veo.
Ok. Por favor, me dices, no sé cómo, cuando quedan 10 minutos, porque no tuve tiempo de adaptar la charla cuando me dijo Duván que es de 50 minutos.
Ah,
Y
ok, profe.
no tuve tiempo de adaptarla y no tengo la fuerza. Entonces
Ok, ok.
me toca improvisar un poco. Y si me haces una señal, ¿cómo lo harías?
Si quieres, te hago así.
Te quedas, te
Sí, sí,
veo, te
sí,
voy
sí,
a ver.
sí, sí,
Ah,
sí,
ok,
sí,
sí.
sí, yo me quedo aquí.
Entonces,
Ujú.
quizá cuarto de hora antes del final,
Vale,
así puedo adaptar.
vale, vale, profe.
Gracias.
Tranquila, profe. Yo te hago una señal.
No veo a nadie, entonces no veo el público. No voy a ver el público.
¿Pero me ves a mí? ¿De pronto?
Sí, a ti te veo, pero
Ok,
no sabré con quién hablo.
vale. Eh, Tenemos participantes en la llamada de Zoom, solo profesores, los speakers y los
Sí,
shares,
sí, entendí eso.
y el resto están en YouTube.
¿Y cuántos son?
Ahora estamos 22 en YouTube.
Ah,
Ah,
no mucho, no mucho.
sí, sí, somos 22 por el momento en YouTube.
Ah, yo pensé que más.
Sí, ahorita apenas antes de que comiencen las charlas se comparte todo de nuevo y bueno, 23 y así van subiendo.
Ah, ok, ok, ok.
Ujú. Sí, profe.
Sí.
Ok, yo creo que I think we can start now.
Voy a hablar español, ¿no? Pues pensé en español o lo hago en inglés. ¿Qué hago?
Ah,
¿Lo tengo escrito en español? ¿Qué hago?
ah,
Igual, me da igual.
como tú quieras. Si quieres en español y lo presentas en inglés, I think, yo creo que es mejor en inglés, pero las
Es
diapositivas en
mejor en
español.
inglés.
Sí, sí, pero las diapositivas en español funcionan perfecto.
Entonces, ok, voy a dar voy a decir un par de palabras en español y después paso al inglés. Entonces, si es mejor en inglés, a mí no me cuesta ningún esfuerzo.
Vale, profe, sí, gracias. Ok, I think voy a comenzar, voy a dar un pequeño discurso y luego comenzamos. Vale. Hello, everyone. It's a pleasure to introduce Professor Sylvie Pecha. She is a professor at the University of Potsdam and is internationally recognized for her outstanding contributions to global analysis, spectral geometry, pseudo-differential operators, non-commutative geometry, and mathematical physics. Her research has played a fundamental role in building connections between analysis, geometry, and quantum field theory. Today, Professor Pecha will present her talk entitled De lo infinito a lo finito. Before we begin, I would like to mention that Professor Pecha is not feeling well today, but has very kindly made the effort to join us and give this lecture. So we are truly grateful for her commitment, and we kindly ask you all for your understanding and patience during the presentation. Professor Pecha, thank you very much again for being with us, and you can start. Thank you very much.
Thank you very much. Voy a decir un par de palabras en español porque yo pensé que me tocaba hablar español. Entonces, muy buenos días. Estoy en China, Wuhan, China, donde son las 11 de la noche y acabo de despertarme porque tengo un dolor de cabeza un poco fuerte. Entonces, voy a hacer un esfuerzo, pero no prometo nada. I was now asked to turn to English, so I'll turn to English. I thought I had to do everything in Spanish, so I'd prepared everything in Spanish, but now you'll have the slides in Spanish and the talk in English. So thank you very much for your patience if I say things which are not quite correct because my head is not functioning very well. And what I want to talk about is based on joint work with two Chinese friends and colleagues with whom I've been working with for 20 odd years, I would say. So their names are on the slide, Li Guo and Bin Jiang. And so had I known it would have been in English, I would have told them, but it's a bit late for them. I don't think they speak Spanish. Okay, so maybe, I don't know whether you can interrupt for questions. We'll see what happens. So wait a minute, now I'm having problems. Oh yeah. Okay, so what we're going to talk about is how to make the infinite finite. And it sounds like a strange question, but it's in fact at the heart of contemporary mathematics and physics, how to extract a finite part from an infinite, or you could say divergent expression. And it's as old as Euler, even older probably, and we'll then jump to Feynman. We'll see how. So what do Euler, Riemann, both no, Euler was Swiss. I was going to say German. Euler was Swiss. Riemann was German, and Feynman American. What do they share? So here are their portraits, and you can see they're from different centuries. So what do they have in common? So the leading idea is that there's a common scheme to the three approaches or the three ways to deal with infinities, namely extracting a finite part from an infinite or divergent part. So extracting a convergent part from an infinite divergent part. So you back to school material, you've probably remember well when you first met the harmonic sum, Euler, sum with k running from 1 to infinity of 1 over k, the zeta function of Riemann, and if you take s equal 1, which you're not allowed to do in principle as it stands here, because you have to take the real part of s larger than 1, but assume you were taking s equal 1, you would find again the harmonic sum. And this integral, which if you're not familiar with physics might look a bit strange. So the convention later probably is that this k, which is in Rn, the absolute value stands for its norm, and in physics you don't write it. So if ever you see k2, it means norm of k to the square. M is the mass, and I'm assuming it's non-zero, because otherwise I'd have an infrared divergence, so a divergence around 0. I don't want it. Here, there's a divergence at infinity, because the 2 is smaller than the 4, more or less. Okay? So that's the kind of thing, that's a very down-to-earth example of the kind of thing we are looking at. Can we assign to all these expressions a finite value? And then you might ask why. And the answer is yes, but yes and no, because yes, you can assign a finite value, but it's not very satisfactory because the finite value depends on the method you use, as we'll see. But why do you insist on extracting a finite part from a divergent expression? Because you could say, at least for me, one of the essential applications I see is that you want to measure the surrounding universe. And for that, this is supposed to picture particle accelerator, and you feed it with some data, but you can't just feed it with infinities. You have to feed it with formulas which will spit out some finite quantities. So you have to deal with these infinities, which are everywhere. In fact, I think mostly we're confronted with infinities when we want to describe our universe. So let's go back to the harmonic sum. And I suppose you also remember from long ago, maybe for most of you, I'm sorry about the LaTeX, which is not perfect, as you see, but I did my best. So the red part is supposed to be what you want to get rid of. Why do we want to get rid of this log n? We're summing 1 over k from 1 to n. As a matter of fact, we wanted to sum it from 1 to infinity. So we want to let n go to infinity. And for that, we have a problem because log of n goes to infinity when n goes to infinity. And Euler had already spotted that out, and he just took it, subtracted log of n, as I put in the circled or squared formula. You extract a log of n, you subtract it, and what you get, a very famous constant, the Euler-Mascheroni constant. And this constant is still very mysterious, so all this is still not completely understood. And Riemann, a century later, as we saw, did the same thing, but from another point of view, introducing the famous function which carries his name, the zeta function, and recalling our first university steps, we know that this sum k over minus s, k to the power minus s, from with k running from 1 to infinity is convergent for real part of s larger than 1. And unfortunately, we want it for 1, so that's bad luck for us. And when you let the sum, which you find for real part of s larger than 1, when you do an expansion, a meromorphic expansion at 1, you find what's written below at the bottom of the slide. And the red part is, again, what you want to get rid of because we want to evaluate it at 1. So 1 over s minus 1 is not really a good choice. But that's okay. I'm sorry. I tried to repair this just before the talk, and it didn't. Oh, sorry. So wait a minute. So you can't see the last formula, but it's a good exercise to guess it. So you take the difference, zeta S minus 1 over S minus 1, and you let S go to 1, and this goes to gamma. So they found the same gamma, which is reassuring. But we'll see that it's not that reassuring because everything depends on the scale you use. So if instead of summing from 1 to n, I summed from 1 to kn, where k is an integer, then because the logarithm is additive on products, I would get log of n plus log of k. The log of n should be in color, by the way. And oh, there's a mistake. There's a mistake. I hope you see it. Then the sum, so we're taking again, so there's a, the colors are wrong. The red should be log of n and not log of k, and I should be extracting log of n in the squared formula. Sorry for that. And if I subtract log of n, as I did before, the divergent part, I unfortunately don't get gamma, but I get gamma plus log of k. But it's just as reasonable to take the sum from 1 to n as to taking the sum from 1 to kn. So there's this ambiguity we're confronted with. And the same thing for the zeta function. If I multiply by mu at the power s minus 1, then I get a log of mu. Again, this shouldn't really be in red, but okay, it doesn't matter. And the divergent part I take away as before, 1 over s minus 1. And what do I get? Gamma plus log of mu. So if I take mu equal k, I get the same thing from Euler's point of view and from Riemann's point of view, if you like. Okay, I hope it's okay. If there are any urgent questions, let me know, like, why did I put log of k instead of log of n? That's a mistake. Now let's go to physics and Feynman diagrams. This is the Feynman diagram, uninteresting, very uninteresting, for the void. It's just a circle, it's just a loop. And every one of these introduces a factor 1 over the norm of k to the square plus m2. I'm assuming we have mass, again, because I don't want to deal with two types of divergences, infrared and ultraviolet, infrared being for k equals 0, ultraviolet being for k going to infinity. I don't want to deal with both because I can't. When you improve one, you make the other one worse. So I don't want to, and it's not just me, it's a real problem. So that's why we put a mass which is non-zero, so that we don't have two problems to deal with, only at infinity as is. I don't know whether you see this hand. Do you see the hand? No? Okay. Do you see? Yes. Okay. So this diverges again for the same reason I said at the beginning, because 2 is smaller than k. This is a exercise, analysis first one exercise. And now I introduce a regularization. This is the way physicists would do it. I put an epsilon, I put a factor in the denominator, k, norm of k to the power minus epsilon, and I'll let epsilon go to 0, which will give me 1 in the numerator, and all the rest as well. You see, I have a 2 pi 4 minus epsilon. When epsilon goes to 0, goes to 2 pi 4, and mu to the power epsilon, when epsilon goes to 0, goes to 1. So indeed, I epsilon m tends to Im when epsilon goes to 0. Now, if real part of epsilon, why did I introduce epsilon here? If the real part of epsilon, which you can assume is complex, is larger than 2, then you have convergence. And you could show that there's an analytic continuation at epsilon equals 0. I suppose it's written below, but now we'll skip that, too bad. And here is the expression again. The first line is just copy paste. And the second line, I'm changing variables. I'm doing a change of variable, r equal mt. That's just to get rid of the m and to go back to maths where we have 1 plus t2 instead of m2 plus t2. And then you can recognize, if you're familiar with it, with a beta function. You can recognize a beta function. So it depends on 2 parameters. It's defined in terms of gamma. Here it is. B of xy equal gamma x gamma y over gamma x plus y. And the gamma functions admitting meromorphic continuation, we get a meromorphic continuation of our I epsilon function at epsilon equals 0. Okay? M is fixed. And so we write the Laurent expansion at epsilon equals 0, and we find this expression, which is maybe not that amenable, but that's typical of Feynman integrals. They quickly get complicated. Doesn't really matter. What matters to us is what is in red. We want to get rid of what is in red, the divergence, and keep the finite part. And the finite part is the good part, is the blue part. So I've kept the blue part. And as you see, I put a mu at the beginning, you might have noticed, and everything depends on the mu. If I rescale mu, I get an additional term. So all this is relative to the choice of parameter you make, which is not reassuring. You don't really want that. But physicists are used to dealing with such problems. That's the whole discussion in renormalization, which I won't dwell into right now. So now I'll seem to be doing something different, but it'll be in fact very, very much related, is to count integer points on cones. You might think, why do that? I just say a word. I won't say the whole story. It was inspired by work by Michel Vergne and Nicole Berlin on toric geometry and on the Todd genus for toric varieties. So it's inspired by geometry. I can tell you the story if we have time afterwards. So we take a convex cone. So it's like an ice cream, but in fact, it's not quite like an ice cream. It's not a round ice cream. The section is not an ellipse. It's a polygon. Because if you had, for example, a circle as a section, it would be very complicated. Calculating the number of discrete points in a disk is a complicated problem. That's not our problem. And you can describe a cone, soon we'll have pictures. You can describe a cone as an intersection of hyperplanes. This is what I call the H form. So I'm now showing with my hands because you have not a round cone, but you can we'll see an example. You can describe it as the intersection of half spaces. And so there's a closed and open cone according to whether you take or not the boundary of the half space. And you can describe it in terms of generators. The generators are the vectors generating what they call the sides of the cones. It's not called like that. I'll find the word. And so a very deep theorem says that any polyhedric convex cone can be, let's put it closed, that doesn't really matter, can be described both in the form H and in the form V. So either as an intersection of half planes, half spaces, or as generated by vectors. I think we'll see an example now. So let's take two generators, 1, 0, we're in R2 with the orthonormal basis, a canonical orthonormal basis, E1, E2, and we take E1 and E1 plus E2 as our two generators, and then all I've said before is that we take non-negative linear combinations of these two. That's in the form V, and in the form H, you'll have this description that x2 is non-negative and x1 minus x2 is non-negative. Oh dear. And then you can guess the last part. It's very good like that. It maintains your attention, that you can guess that the inequalities will become strict. Here it is. Whether I keep the dark green lines here, this one or this one, is whether I take the closed or open cone. And what we want to do is to count the points of the lattice C intersected with ZK. We could take another, ZK is a lattice, so I'm saying it wrong. We want to count the lattice points of the cone. And for that, we take a lattice. Here, I've taken a very simple lattice, ZK. I could take another lattice, but it makes it a bit more complicated. I'm not going to go into that now. And let's take this very simple cone, 0 plus infinity. So it's R. So it's all the non-negative real numbers. That's a cone. And so if you take the open cone, is the positive real numbers. And if you take the intersection with Z, you have the positive integers. And in 2 dimensions, a nice one is this Chen cone. We'll call it Chen. You'll see why, maybe. I'm not sure we'll have time to see why. It's generated by E1 and E1 plus E2, and the intersection is with the lattice, with Z2, consists of pairs m plus n, with mn non-negative. And now we want to count the integer points in C intersected. Well, no, okay, this sentence is not quite correct. It's correct, but it's redundant. I want to count the integer points in C, which amounts to counting the points in C intersected with ZK. Or said in another way, how do I give a meaning to the sum over all these points of the expression n to the power 0, which is 1. Sum of ones over a set is counting the number of points in the set. Okay? So I'm counting the number of points, of integer points in a cone. Okay? And that's our question. And it looks like it's stupid and hopeless, but it's very deep, in fact. So that's our question, how to calculate this. And we're going to use yet another way, is the exponential regularization, which is very much used in maths and in physics. For example, in index theory in physics, in maths, if you're a geometer or a topologist. So it's based on the fact that e to the power 0 is 1, and the exponential is continuous at 0. So e to the power minus epsilon n, when epsilon tends to 0, tends to 1. And now we're replacing, remember, we want to define the sum over the integer points of the cone. We want to define this sum of ones. It's hopeless because, of course, it's infinite. The cone is infinite, so we'll have infinitely many points. We're turning into a less hopeless issue, namely, we're replacing the 1 by an approximation e to the power minus epsilon n. So that's what we're actually computing. And this sum, you know, this is a geometric series. And so it's a very simple expression. And if you're familiar with the Todd function, you might recognize in the background that the Todd function is not too far. But unfortunately, but that's expected, there's a divergence where we left it. Remember, we wanted to sum the ones, and we cheated, we replaced 1 by e to the minus epsilon n. It's okay as long as epsilon, that should be said here, it's okay as long as epsilon is positive. But if epsilon is equal to 0, we have a problem. And again, we have a divergence. We take it away, and I forgot to say FP is finite part. I've already used it several times. It's taking away the divergent part minimally. I could take everything away. For example, I could take this away, subtract this, but then I would get 0. Or I could get rid of everything. And I like to compare this with what I imagine going to the dentist in the Middle Ages was like. I suppose the dentistry was not very developed, and they would just take out the teeth that were spoiled or that were damaged. So they would take out the damaged teeth, and you might as well take out minimally, not taking out the good teeth. And that's what we're doing here. We're like a medieval dentist taking out the bad teeth and leaving what's rescuable, namely this minus 1/2. So we get, if we do that, we get minus 1/2. So that looks very strange, because remember, we were summing ones over, we were taking infinitely many ones, and we get something negative and something non-integer. It's a bit disheartening. So it looks as though it's getting worse and worse. And now let's do it in 2 dimensions to see what that gives us. At least, even if it's very strange, we should have something in 2 dimensions which seems compatible with what we have in 1 dimension. So let's see. We're counting the integer points here. So C1 is open. I think I decided it's not very clear. I think I should put a 0. We'll see what I do afterwards. I've forgotten. So it's the integer points in here, and I think I leave the ones on the boundary out. Let's see. Yes, so Z plus means I'm taking out the 0. So here it is. There should be a comma here between those two. And if I change variables, as I claim here, we get this. And when you do this, you find 2 independent sums, 1 over m and 1 over n. So you find the ones we were working with before, this one and that one. And so notice the difference. This depends on 2 parameters. This depends on 1. Okay? And so now we remember that we had, so I don't know whether you remember, we had this formula. So this amounts to saying that it's a holomorphic function at 0 over epsilon. If you think of it 2 minutes, simplifying this, looking at it from afar, comes down to claiming that it's a holomorphic function at 0, or holomorphic germ, over epsilon. So we go back to what we've got. So here it is, holomorphic function of epsilon 1 over epsilon 1, holomorphic, the same one, of epsilon 1 plus epsilon 2 over epsilon 1 plus epsilon 2. So in the end, we don't really care for the moment what we have upstairs. The blue, I recall, is good, and the red is bad. So the blue is holomorphic at 0. That's the idea. We're only focusing on 0 because that's where we want the limit in the end. We forget about the rest, so we're talking about germs, not so much functions. And so if you look at the singularities, you say epsilon equals 0, epsilon 1 equals 0, epsilon 1 plus epsilon 2 equals 0. and it's linear in the variables. So we get a meromorphic germ with poles linear in 0. Let's remember this. It's of course, the expression here is not linear as a whole, but it's products of linear forms in the epsilon I, and that we have to remember. So let's see what we do with this. So this is a recap. So now we're doing it more in detail. So remember, I had this formula I just showed you again of, remember that this is S epsilon, this is, what did I call it? S0 epsilon 1, and this is S0 epsilon 1 plus epsilon 2. Not quite, there's this factor. And if you, I'm not sure, I think I'm wrong. Here, that's strange. I've left a version with mistakes. So this should be epsilon 1 plus epsilon 2. There's a mistake here. And so you just get the product of what you had in one variable. One here, one there. It's the same type of expression, 1 minus 1/2, minus 1/2. It's just the variables now have changed. Epsilon 1 for this one, epsilon 1 plus epsilon 2 for this one. And when you do all that, you build a product, you expand, you find this. And so you think, oh, that looks good, I'm done. I get rid of the red ones. Okay, this looks rather red, not quite red because there are things on top, but let's get rid of it because I'm not sure whether they're rotten teeth or whether they're still healthy teeth. So I'll take them out just in case, and I'll keep 1/4. So it's still a question mark. Is this legitimate or not? Wait a minute, I'm getting rid of something which doesn't enable me to see what I'm... I can't see what... I think you can see it, but I can't see... Oh dear. I can't see the bottom formula. Just a minute. It's KI, which is wanting to help me, but it's getting in the way, and it's hiding this part. So I assume I can't see what I'm talking about, but I assume it's 1/4 plus etc. So the finite part would be 1/4. Okay, I'm not sure what this is. Let's see. And then maybe it was the question. Okay, it's a question. Is 1/4 really this quantity? So we're now going to be more suspicious, and we're going to be a little more systematic and use the geometry of cones. So in our group of 3 co-authors, there's Liguo, who was a number theorist, still is, but is also a combinatorist. There's Bin Jiang, who is an algebraic geometer and also much more. And he knows cones and the geometry of cones, he's more familiar with it than we are, because in toric geometry, you use that in an essential way. So yes, strongly convex just means there's a point. It's really a cone. It's not just there's a top or a bottom to the ice cream. So now we're going to subdivide. So that's the geometry we're introducing. We're going to subdivide the quarter space. The quarter space spanned by E1, E2. I mean, this part, quarter cone, it's a cone. It's the cone spanned by E1, E2. We're going to split it into 3. C1 here, the diagonal, E1 plus E2, and C2. And this is a subdivision. We're subdividing the big cone into 3 smaller, in inverted commas, they're just as infinite, cones. And you can either take into account the diagonal or not taking into the account the diagonal. So here, I'm forgetting about the diagonal. It's an open subdivision. Here it's a closed subdivision where I don't forget the diagonal. So think of the difference between integrating and summing. If you integrate, you don't, this diagonal is one-dimensional, whereas the cones are two-dimensional. And so if you integrate, you don't see the one-dimensional part. It'll be zero in the integral if you integrate in 2 dimensions. Whereas if you sum discrete things, then you will see the diagonal. And so it was the opposite I should have said. So you'll see the diagonal. So that's why we have to keep it in mind, whether we do include it or whether we don't include it. So let's go to the Laplace transform of the cone. It's a kind of generating function. It's a way to describe the cone. It's a kind of dual function, so it describes the cone as well as the cone itself. It's enough to understand a cone, as long as you take it for all epsilon I positive. So this is a scalar product, epsilon x, which is sum of epsilon I xi. So in one dimension, we said at epsilon 1 equals 0, remember we want to set epsilon equal to 0. That's the idea all over. For epsilon 1 equal to 0, we have 1 over epsilon as a pole. At 0, we have 1 over epsilon 1. And so that's the pole. You see the similarity. There's a generator E1 and a pole 1 over epsilon 1. So there's a similarity between the two. Now we're going to the two-dimensional one, generated by E1 plus E2. It's always the same one we're looking at. And we've got two hyperplanes, hyperplanes of poles, sorry. Epsilon 1 equals 0, epsilon 1 plus epsilon 2 equals 0. And again, you see the similarity in the structure. So I can't see what you see. It's hidden by this KI thing, this AI thing. And so I can't see the bottom, but there's a similarity between the shape of the singularities and the generators. Yes, okay. And then, let's see, C2. I take another one. Remember I had C1, C2? I had this one and that one, so I'm taking first this one and then that one. This one is generated by E1 plus E2, and the other one is generated by E2, E1 plus E2. And so I do that, and again, I'm not surprised. I see the same pole structure here as reflecting the generators of the cone, okay? So when you do this in a much more general context, I'm not going into the details. It's a simplicial cone, which means that this is these vectors are linearly independent. Then you have this kind of formula. You only need to remember, you see, again, the generators, these are the generators, they're there again, just like we had them before. And this is a scalar product, epsilon. So there are n generators, but each of them is a vector in Rk, and epsilon has k components. This is a scalar product, and there are n of these in this product. So let's go back to this one. You see, this would be the sum of epsilon. Let me see what I'm saying. Yes, this would be epsilon, a scalar product E1, and this would be epsilon being epsilon 1, epsilon 2, scalar E1 plus E2. I hope I'm saying that correctly. I'm not sure now. Anyway, we have poles, and okay, this subdivision, and you see the geometric subdivision gives algebraic subdivision. So LC1, so this is a cone. So LC1 is this expression for C1. it comes from what I wrote before. It's just this. It's the Laplace transform. So it looks like this. You have LC1 of epsilon 1, epsilon 2 here, LC2 of epsilon 1, epsilon 2 here, and the product of these two expressions, LC0, epsilon 1, LC0, epsilon 2. This corresponds to this decomposition, which we learn in high school, in fact, and maybe again at university. And so we have a new pole. So here you see we just have poles epsilon 1, epsilon 2. That's if we look at this big cone, okay? This it corresponds to the generators. Here are the poles. Now, this decomposition gives us a sum by which a new pole arises, epsilon 1 plus epsilon 2. And you notice, because we were working with an integral, there's this part doesn't add another term, which we'll see very soon. This is because we're working with integrals. The integral on a one-dimensional space, the integral in 2 dimensions of a one-dimensional subspace is 0. So now I'm looking at sums, discrete sums. So now you see I'm a bit more careful. And you see we have, wait a minute. Yeah, we have the ones we had before. These are the ones. This is C1, this is C2, but we have an additional term coming from that, because in the sum, you can't forget the one-dimensional space cone. You can't forget it. And so you have a similar formula. It's again, a geometric subdivision gives you an algebraic subdivision, and the finite part accordingly has 3 terms. So what do we find? We find, now I can't see a thing, we find 0, I think. Is that right? You have to confirm, I can't see it just now. So is that, yeah, 0. So it's a shame I can't see it. I don't know why I can't make it disappear, this thing. So I have to guess. I've forgotten now. The first one is minus 1/2, I think. No, 1/4, and minus 1/2. So 1/4 we computed at some point, if you remember, 1/4. This gives you 1/2, minus 1/2 gives you 0. So it's again a bit misleading. You find that the number of points here, this regularized, renormalized, whatever you want to call it, number of points is 0. So wait a minute, now I have to get back to, yes, that's what I wrote here. But on the other hand, so remember we have this form, we have this, that was this subdivision property. And so we've computed this side, taken the finite part as epsilon goes to 0 of this part. Let's do it on this part. And this is simpler. So, you think, okay, the finite part should be the product, the finite part of a product should be the product. No, yeah, the finite part of a product should be the product of finite parts. You would like it to be. And if you do that, assuming that, then this thing gives you minus 1/2 to the power 2, which is 1/4. And of course, it's not the same. So from a formula which was correct, that was correct, as an equality of meromorphic functions, you get to if you do things naively, you get, namely, if you take too many teeth out, more or less, and are not careful to keep the healthy teeth, then you find yourself with a very strange formula, 0 equals 1/4. So that was not the right thing to do. And in physics, you call that to cure divergences. So that's why I like to compare it with dentists, because I really think physicists think in terms of, in medical terms, when they say you cure divergences. So now we're going to try to be a little more subtle and not take out too many teeth, making the mistake of extracting a healthy teeth among the other damaged teeth. So for that, and that's where our work with Bin Zhang and Li Guo comes into play, inspired by the work of Nicole Berlin and Michel Verne, because they used a scalar product, the notion of orthogonality. So what we did, a mistake we made without realizing, is that we did things like epsilon over epsilon equals 1, which is true. But so epsilon over epsilon, when epsilon is non-zero, equals 1. But when you let epsilon tend to 0, it still goes to 1. But did you really want to keep this? Was it not a slightly rotten tooth, or did you want to keep that tooth because there's a 1 over epsilon? If I recall what we went through earlier on, I said, let's be bold and let's get rid of this. You see, it's a bit like what I've just described. It's something going to 0 over something else going to 0. And sometimes this converges, so you don't know whether it's a bad tooth or a good tooth. You don't know. And we just boldly got rid of them, which is maybe better in the long run, but maybe we should have been more careful and could have kept them. And so this is a way to be a little more subtle and maybe keep more teeth in one's mouth. And so we start again. We do the same thing. So I have how many, 5 minutes, or how much do I have?
Yes, Professor, you have 5 minutes and then questions.
Okay, thank you. So I won't get at all to the end. I don't know why, but it doesn't matter. The main thing is to convey an idea. So we'll convey one idea here. You see, so those are the expressions we had before. This is S0, I think I called it, SC0, I think I called it, of epsilon 1. This is, so again, I think I make a mistake here. I think it's epsilon 1 plus epsilon 2. I have to check. It's a good exercise. You can check afterwards. And so we find this times that. And remember, I just showed you, we got rid of this. Remember? And now we're going to inspect this more carefully. In getting rid of that, we were left with 1/4. Now we're going to look into that more carefully. This we get rid of. This is obviously rotten. We just get rid of it, but this was not so obvious. And we're going to be more subtle and rewrite it. So I'll write the whole thing. So we're writing, let me see what we're doing. We're writing epsilon 1 as half of epsilon 1 plus epsilon 2 plus epsilon 1 minus epsilon 2. I can't write here, but this epsilon 1, I write it as half the sum of this and the sum of that. And in doing that, I get this. Now I decide these are really rotten teeth. This is really a rotten tooth because epsilon 2 is corresponds to the generator E2, which is orthogonal to the generator E1. Here I wrote that. And you see E2 is in blue, E1 is in red. And this one is orthogonal to that. So in a sense, they're not simplifiable. They're not reducible. They're not, you can't do anything about these bad teeth. You have to extract them. And that's why so now we get rid of something different. It wasn't what we had before. We don't get rid of this because this is not orthogonal to that. E1 is not orthogonal to E1 plus E2. So we get rid of different parts and we find 3/8. So it's different from what we had before. And now, maybe we could finish on a positive tone. We are relieved because remember we had the naive way when we extracted the wrong teeth, maybe we could say, I'm not sure. We have to think in terms of teeth, what it meant. If we now do the same thing, compare, this was with the subdivision, if you remember. Subdivision, I'll just go back just so that it's, where is it? Here we have this subdivision, and it led to 3 terms, if you remember. And now we've dealt with them differently, and we've got 3/8 instead of 1/4. Before we had 1/4, 1/4. Now we have 3/8, and minus 1/2. As a whole, it gives you 1/4. And this is indeed what you get on the left-hand side. It's 1/4. So you're relieved. Oh dear, there's a mistake here. There should be an equal where the hand is. There should be an equal. We've got indeed that the extraction of the finite parts is using this scalar product is indeed, let's say, the extraction of the finite part of the product is indeed the finite part of the, no, I haven't said that right. The finite part of the product is indeed the product of finite parts, if you're careful, as we were here. And since I have to stop, I'll just say a bit about Michel Vergne and Nicole Berlin's work. That's so it's yes. So I'll compare it to work done by Alain Cohn and Dirk Kreimer. Alain Cohn, who built the non-commutative geometric school, and today together they dealt with expressions like that, much more complicated. And what they did was use the same parameter, epsilon 1 equals epsilon 2 equals epsilon. So they use the same one. So they find themselves with expressions like epsilon over epsilon, which we said was 1, goes to 1 when epsilon goes to 0. And so in doing that, they left teeth which were not really healthy, which were half healthy. And they had to use a co-algebraic device, Hopf algebras, co-products, to undo these mistakes, to unwrap these mistakes and correct them by counter terms. Here, following Berlin and Verne, we never make these mistakes, because in introducing first keeping several variables, not just one, we can keep in mind where they come from. Following Alain Cohn but not just them, most physicists work with dimensional regularization, which uses one parameter. If you forget when you identify epsilon 1 with epsilon 2 and call it epsilon, then you identify these parameters and you forget where this one came from. It came from one divergence, one cone, and this one came from another cone. You forget, whereas we never forget. And to never forget, you should never forget that they're orthogonal. You could take another scalar product, not the conventional canonical scalar product, and it would depend on that choice. But that's the idea. So it's complicated because we have meromorphic functions in several variables, which is tedious. But it's worth investing work and using meromorphic functions in several variables, because then you don't make mistakes and have to correct them with a very complicated co-algebraic, very beautiful but complicated co-algebraic device. Here we just, it's very naive. We take out the rotten teeth. We don't have to think, is this really rotten? Is this not really rotten? And so, yes, so there's no obstruction. And let me go to the last slide. So I won't look into all this, but I'll try to go to the last slide, or conclusiones. Okay. Okay. So maybe Okay, I can't do that. It's too, no. So that may be the conclusions, and I'll stop. Using meromorphic functions with linear poles in several variables unifies renormalization of discrete sums over cones and Feynman integrals. You can look at them in the same way. The geometric focus on renormalization is through the choice of a scalar product. You can say it's a weakness. We make a choice. It's a bit like choosing coordinates. So, but it's a geometric way of making a choice, let's say. It's a geometric choice. And then you have a renormalization group, which is indeed like, in the spirit of Kohn and Kreimer, a pro-unipotent group. I won't say what that is, doesn't matter. Now there are open questions you can ask. What happens if you have two different scalar products? Can you relate them? Can you relate the transformation groups, which I haven't had time to talk about? It's for people who are familiar with that, it's related to renormalization groups. Yes, they are isomorphic. We could show that. But then how can you relate the finite parts you find? That's more difficult. How do you relate what we call a renormalization group, which involves several variables, with the one of Kohn and Kreimer, which involves one variable? We don't really know. We have ideas, but we don't really know. Are meromorphic functions with linear poles? Linear, remember, we just had linear combinations of the epsilon i's. Are they enough to describe all the divergences we'll come across? And recently, well, now for some years, we've been working on that. We're supposed to finish in the coming weeks. We've been looking at cyclotomic multi-zeta generalizations of cyclotomic multi-zeta functions. For those who know, they'll recognize the words. We're looking at cyclotomic multi-zeta functions or sums on cones. And we saw, because of the cyclomicity, I don't know how you say that, because of the complex variables entering the cyclotomic multi-zeta functions, we have polylogs. So we have logarithms in the divergences. So we don't have it's not enough to look at linear poles. We need to look at logs. But we're preparing for that, and we're working hard. It's quite hard work. Thank you very much for your attention. Sorry that I talked too long. Thank you.
Thank you very much, Professor Sylvie, for your nice talk. Now we are open to questions in YouTube. Let me check the YouTube. Yes, we have some questions here, so I will read them now. Thank you for your talk. What changes if one replaces set k with an affine lattice a set k plus a?
ZK plus affine. Yes, you're right.
Affine, yeah, affine.
Affine. Yes, you're right. Very, very pertinent question. So we haven't dealt with that, but implicitly what we're assuming is what Berlin and Verne also do. You can always reduce to linear lattices. So you can always use, if you look at the generating function, it just introduces a multiplicative term. If you look at Berlin and Verne's papers, you'll see that everywhere. It just translating by a vector to go from a linear one to affine one, just translates. So this translation just introduces a multiplicative term, which just follows all the computations. You just take it with you, but it doesn't change the heart of the matter.
Okay. There is another question by Miguel Reyes. Thank you for your presentation. When counting the points on the cone, did you try to apply generating functions?
Well, those are generating functions. They are. Those are exactly the generating. Oh, I'm not sure I understand the question. These are what I call Laplace transform. Maybe I don't understand the question. These Laplace transforms are the generating functions. Is that what? Maybe they, I don't know, they were there. So either a discrete one, I mean, obtained by a discrete sum, discrete Laplace transform, or obtained by a continuous Laplace transform. Both, they're two types of generating functions which give you two types of information. The continuous Laplace transform gives you purely polar information. It just gives you the poles. And the discrete one gives you much more. If you are familiar with the Euler-Maclaurin formula, the two generating functions relate by the Euler-Maclaurin formula for cones, which is in fact the title of one of the papers by Berlin and Verne that inspired us.
Okay, Professor. We have two more questions. I think I will do it really fast. So perhaps this is just a naive question, but do you envision any applications of your work, for example, in physics?
Oh, naive. I will say something strong. It's a perverse question because it's saying, what is this useful for? Yes. So we were inspired in physics by the work of Speer, Eugen Speer, whose work, who introduced analytic renormalization in the 60s, if I'm not mistaken, 60s, 70s, I'm not sure now. And analytic renormalization is similar to what we do. Namely, he used several parameters. And seeing how difficult it was, it's still taking us a huge amount of time and energy to work with these multi-variable meromorphic functions. I wrote to him one day, realizing that he was still alive, and asked him, why his approach. I didn't say it like that. I said it more diplomatically, but more or less asking him why his approach had been abandoned, more or less, because people don't use analytic renormalization so much. They use dimensional renormalization, which is in one parameter. It's just one parameter. And he answered, I suppose it was too difficult because of meromorphic functions in several variables. But in fact, he proves, so this answers the question in part, maybe, he proves that all the amplitudes in a series of papers, all the amplitudes for oh, wait a minute. I think it's probably polynomial interactions, physical systems with polynomial interactions. I have to check. He proves that the amplitudes give rise to these meromorphic functions with linear poles. And he gives the structure of the poles. In fact, I name him here, I think. I saw Speer. You see, Speer, maybe I'll say, yeah. So Speer, yeah. And another person I'd like to quote here is Viet Dang, who happens to be in Wuhan with me. He, in fact, substituted me today for my lecture because I was ill. So Viet Dang and Bing Zhang worked together on Feynman integrals on manifolds, inspired by the work by Speer and by what we did together with Bing Zhang and Li Guo. So, and you see, the linearity is simple. It's just sums of epsilon i's. There's no coefficient. Okay, no, there's only coefficient 1. And that's typical. Whereas in Berlin and Verne, at the bottom of the slide, for general cones, you have coefficients. So their point of view is much more general. It includes kind of Feynman integrals. But as I said, we can't yet compare what we do with what directly. We can compare in some ways what we do with what Durkheim and Alarcon did, but we can't compare it directly. We still are missing a direct comparison. So it's a yes and no answer to your question.
Okay, Professor, thank you very much. I have a question, but I know that you are with a headache, so I do not
No,
want
but it's
to
okay.
disturb
It's
you.
okay. When it'll come back afterwards when I stop speaking.
Okay, so I will ask my question and then thank you very much. So you mentioned at the beginning this thought genius in the historic setting, in the historic geometry. Is it appearance here related to this Riemann-Roch or Atiyah-Singer index theorem, or is it different somehow?
So I'm not a specialist of toric geometry. Wait a minute. Oof. Is it related to an index theorem? I would say not directly.
Okay.
Wait a minute. I'm not sure. Maybe other people can answer this better than me in the audience. I'm sure somebody can answer better than me. It's a good question, but I don't think so.
Okay.
Wait a minute. So the Todd genus is a characteristic, it gives rise to a characteristic class, but it's not related to an index, is it? Someone can say better than me, I'm sure. So I can't really answer. I
Okay.
think no. I think no, but
Okay.
I'm not sure.
Okay,
Especially now
Professor.
with a headache, I'm even less sure.
Yeah, okay, Professor. Thank you. Thank you very much for attending today, even though you are sick. So thank you very much for your time. You have a
And
special
I would
place.
since because I was not too well, I forgot to thank the organizers because I think this initiative is very nice. Thank you. Thank you to you. Thank you, Andrea. Thank you to Duvan and other people I probably don't know. Thank you because I think this is a very nice initiative. Thank you.
Yeah, and thank you very much for always support our initiatives. You have a very special place in our hearts. So thank you very much for all. And
Thank you to you. Thank you to you. Goodbye. I won't attend the other talks, or I'm
it's
sorry I
okay,
didn't attend
Professor.
talks, but I couldn't. Thank
Yeah.
you. Goodbye.
See
Bye-bye.
you, Professor. Bye.
Bye-bye.
So to all of you, our viewers in YouTube also, we will have a 40 minutes break. So we will start again at 12 p.m. Colombian time and 19 Central European time with the talk of Professor Simon Donaldson. After that, we will have the talk of Maria Jose Pacifico. And at the end, we will have our ICMAM Prize 2026. So you are all welcome to join us in 40 minutes. Thank you very much and see you all soon.
Thank you.
See you.
See you. Professor Donaldson, are you there? Okay,
Maybe he wants to check his slides also, so we can ask him.
If not, then we can come back in 40 minutes and
Hello, Professor Donaldson. Are you there?
Yes, hello.
Hello,
Thank you for
welcome. Thank you for being here.
Thank you for sending the link for.
Hello, Brian.
Hello, Professor Nora. How are you?
Thank you for helping me to join.
It is a pleasure.
Thank you.
Maybe we can check if you can share your slides properly
Mhm.
for the time.
Okay. Mm. Okay.
No, I am not seeing.
Oh, I need to share my screen. Sorry, I haven't done that. Hang on. Forgot to share my screen. Let's do that. Hang on. Hang on. Share screen.
Mm. Okay, now you're sharing your screen.
Mm.
Perfect.
Okay.
Can you try to move the slides?
I'm sorry, Brad.
Can you try to move the slides?
With slides? Mhm.
Now it's black. Ah, okay. It's working perfectly. Thank you, Professor.
Okay, that's good.
I want to say that we are just a few here, but most of the participants are attending the talk via YouTube, and we're
Mhm.
live streaming on YouTube. Is that okay?
Okay, yes. Mhm.
Okay, nice. So we are going to wait 5 more minutes, and we can start with your presentation.
Mhm. Well, very good. Mm. Mm. Mm.
Okay, Professor, you're ready? Can we start now?
Right, I'm ready.
Yeah, okay, Professor. Let me introduce your talk. Hello, everyone, again. It is a great honor to introduce Professor Sir Simon Donaldson, one of the most influential mathematicians of our time. He's sharing pure mathematics at Imperial College London and permanent member of the Simon Center for Geometry and Physics at Stony Brook University. His work has profoundly shaped modern differential geometry and topology, particularly through the use of gauge theory in the study of four-dimensional manifolds. He received the Fields Medal in 1986 and was elected a Fellow of the Royal Society in the same year. His many other distinctions include the Crawford Prize, the Shaw Prize, and the Breakthrough Prize in Mathematics. He was knighted in 2012 for his services to mathematics. Today, Professor Donaldson will present his talk entitled Collapsing Special Holonomy Manifolds and Multivalued Functions. Thank you very much for being here with us. Please go ahead, Professor Donaldson, whenever you're ready.
Well, thank you, Brian, for the kind introduction, and thank you to the organizers for inviting me to take part in this meeting. This will be a talk about topics in differential geometry, and this is the overall plan I hope to follow. We'll begin, the first part will be general review of some questions in the revolving convergence of Riemannian manifolds, and in particular collapsing phenomena. Then secondly, we'll move on to look at a particular case of seven-dimensional manifolds with a very special kind of structure associated to the exceptional Lie group G2. And in the third part, if we reach that, we will talk a little bit about some interesting questions in analysis that arise here, and also in other areas of differential geometry over the past few years, involving what you might in brief describe as multi-valued functions with certain kinds of singular branching sets. So let us begin. Let's first of all think, what does it mean to say a sequence of Riemannian manifolds has a limit? This is an interesting question, particularly for Riemannian manifolds with some special properties. For the purposes of this talk, we'll be thinking of Einstein manifolds, manifolds with zero Ricci tensor. So a very general way of formulating this convergence is due to Gromov. It involves the notion of the Gromov-Hausdorff distance, which is formulated in great generality for compact metric spaces. So if we have two of those, X and Y, then this is an obvious notion that you could say of what it means for these to be approximately the same or close, is that there is a homeomorphism between them which only changes the distance functions by a small amount for some small epsilon. But the Gromov-Hausdorff theory is somewhat more subtle than that, and in particular allows X and Y not to be homeomorphic. The basic notion is the Gromov-Hausdorff distance between X and Y, which, this is the definition, is you take the infimum of numbers so that you can find a metric, in the sense of metric spaces, on the disjoint union, which extends the given metric on the two pieces, and such that both X and Y are epsilon dense. So as I say, any point of Y is within epsilon of some point of X, and vice versa. So you can think of this as saying, in place of in the previous notion, for each point x, in x we have a point f of x in y. Now associated to x in x, we have a small set of points in y whose distance is less than epsilon from x, and similarly for y and y. So we don't have a correspondence between points, but we make a point correspond to a small set. If the distance between the spaces is small. So with this notion of this distance function, we have the notion of convergence of a sequence of metric spaces to some limit. And in particular, of course, a Riemannian manifold is a metric space with distances defined by the infimum of lengths of paths between points. So we can apply this to sequences of Riemannian manifolds. But although we start with Riemannian manifolds, in principle, the limiting object could be something quite bizarre, some more less familiar kind of metric space. So another starting point is a fundamental theorem of Gromov, which, at least for the case relevant to us, says if we have a sequence of manifolds with zero or more generally positive Ricci curvature, and if they have bounded diameter, then there is a subsequence which converges in this sense to some limiting metric space. Well, this is a fundamental theorem. The proof is not particularly difficult. Using this essential idea is to do coverings by metric balls, and the fact that by a well-known facts in differential geometry, or there is the Bishop inequality, the hypothesis on the Ricci curvature gives some control of the volume of balls. So let's suppose, as you say, we're discussing, let's restrict to the situation of manifolds with zero Ricci curvature. Then we can always scale so the diameter is 1. We're talking about compact manifolds. But then there are two cases. If throughout our sequence there's some fixed lower volume bound, the volumes are bigger than some strictly positive number, then a deep theory developed by Cheeger and Colding around the beginning of the century and developed further by Cheeger and Neighbor more recently, gives a good understanding of the properties of the limit space. So if we started with n-dimensional Riemannian manifolds, the limiting object is still an n-dimensional space. It's the Riemannian manifold outside a singular set, which is small in a sense. It has codimension at least 4. So this is a well-understood situation from a theoretical point of view, and this is called the non-collapsed case. Just to think about a simple example, which will introduce some facts and ideas that we'll take up later. Let's consider a complex algebraic surface in 3-dimensional complex projective space, a non-singular complex algebraic surface, and let's suppose the degree is 4. So in that case, the Calabi conjecture, proved by Yau in the 1970s, tells us that there is indeed a metric on X with 0 Ricci curvature. In fact, a Kähler metric, which we'll talk a bit more about later. So this is for smooth complex algebraic surfaces, but what happens if we take a family of such things, so defined by a family of polynomials, say Pt of degree 4. So they're smooth for small non-zero t, but when t is 0, we develop a singularity. So we just think of the simplest kind of algebraic-geometric singularity, an ordinary double point singularity. So to be more explicit, if we work in affine coordinates in an affine piece of CP3, and the singularity is at the origin, then we could, for example, have polynomials written in the affine coordinates. We could take the standard model non-degenerate quadratic form plus t times some generic polynomial of higher degree, where Q contains only terms of degree 3 or more. So that the degree there's no linear part, and the degree 2 part is just given by this standard sum of squares. So this is the simple example of a family of surfaces parameterized by t, developing an ordinary double point singularity when t is 0. So the singular affine quadric, if we put z1 plus squared 2 squared plus z3 squared is 0, that can be identified with the quotient of C2 by the map where we take a vector z to minus z. So how do we achieve that? If I take a point with coordinates zeta1, zeta2 in C2, and then I map that by these 3 degree 2 polynomials into C3, then you will see that this is unchanged if we change the sign of the zetas, and precisely gives a 2-to-1 map onto this affine quadric. So what happens, this is not obvious, but what can be proved to happen, is that these Glaby-Yau-Einstein metrics on these complex surfaces converge in the limit to something with a single point singularity, but is not this is a very simple kind of singularity. It's just what's called an orbifold metric. When we lift to the cover, we get a smooth metric. So this is the simplest kind of singularity here, a point appearing inside our 4-dimensional spaces. And one can also understand in detail the behavior of the metrics for very small t close to this nearly singular point, as it were. But we want really to focus in this talk on the other case, the collapsed case, as it's called, when the volume of our sequence of manifolds goes to 0. The diameter is 1, but the volume goes to diff 0. So theoretically, this is a much less well understood case, but we don't really need, for our purposes here, particularly knowledge of any very general theory, but more a kind of a general picture of what one expects. And that is roughly as follows. This is somewhat imprecise, what we're saying, but I think you'll get the overall idea. So what one expects is that the limiting object is a space of strictly lower dimension, say n minus k, and when we're close to the limit, for large I, the manifold has a fibration over this lower dimensional space, where the diameter of the fibers is very small. The diameter of the fibers is of order some small number delta I, which tends to 0 as I tends to infinity. So here we mean a fibration in a generalized sense, but outside a closed subset, a typically lower dimensional subset of the base, then one expects that this is a genuine smooth differentiable fibration. So the fiber is differentiably some given, say, k-dimensional manifold X. So it was me saying that what one expects is the picture looks roughly like we take a fiber bundle, and then as we approach the limit, we're collapsing by scaling down the fibers relative to the scale of the base. But it's not exactly a fiber bundle because we expect in reality to encounter some kind of singular fibers where the picture is more complicated. Well, how about the metrics? What we expect is that if we stay away from this singular set, we take some fixed point away from it, and then we look on a scale in the base comparable to the scale of the fiber, and then we rescale that piece of our manifold. So we take a delta I neighborhood of our point in the base. That's the same as the scale of the fiber. We take the preimage of that and then rescale by multiplying lengths by a factor of 1 over delta I. Then that thing should converge to some product. Converge as I tends to infinity to some product structure on our fiber times Euclidean space. So we get, essentially, we get a metric on the fiber, but extended just by multiplying by flat directions corresponding to the base. And since our original metrics were supposed to have zero Ricci curvature, the metric we have on this lower dimensional manifold on the fiber should also have zero Ricci curvature. So on a scale of order delta I in the base, the structure on the fibers is approximately constant. I mean, this could also be 100 times delta I or 1,000 times delta I, but some fixed multiple of delta I. But on a large scale, the scale of the diameter of the base, we expect that the structure could vary. So at each point in the base, away from this set delta, we have a Einstein metric, a metric of zero Ricci curvature on X. And this way we get a map from the base minus this exceptional set delta into the moduli space of Einstein metrics on X modulo diffeomorphism. And going a bit further, one can convince oneself that this map should satisfy an equation, a partial differential equation, which is somehow the dimensionally reduced version or the asymptotic version of the Einstein equations in n dimensions. So the equation we expect to get in the general situation is that if we take this map, use the induced metric on the base B and a natural metric on the moduli space of Einstein structures defined by the L2 norm on tensors on X, then that should be a harmonic map. And secondly, if we look at the Ricci curvature of this induced metric on the base, that should be equal to something formed by taking the derivative of our map chi and then contracting using the metric on the target space. This derivative is a linear map from the tangent space of B to the tangent space of the moduli space. We can use the metric on the moduli space to contract those indices, as it were, to get something which is a quadratic form on the tangent space of B, which is where the Ricci curvature lives. So that's the kind of outline, slightly imprecise, of the general picture one might hope to see when studying this kind of collapsing phenomenon. But think about that. You can imagine sort of an analogy or situation in real life. Supposing we have a very long hose of length, say about 1 kilometer. So the diameter is roughly a centimeter, that sort of order. So here the length of the hose is the analog of B, and the diameter is the analog of the diameter of the fiber. So we can imagine that over distances of order 1 meter, say, this diameter is essentially constant. Essentially, we have a perfect hose. So the hose is very close to a product of the interval 0, 1 for the 1 meter by a circle of some length of the order of 1 centimeter. Well, this is a weak hose, so we can imagine that due to the stresses and strains, the diameter changes slowly as we vary over its whole 1 kilometer length. So we can imagine that if we go, say, a distance 10 meters, the diameter might have changed somewhat, for example, from, say, 0.5 centimeter to 2 centimeters. So what we expect then is we get a function on the interval from 0 to 1000, parameterizing the whole length of the hose, which is defined by this slowly varying diameter. And we can imagine that there might be some differential equation which determines this function depending on the physics of the situation exactly. But that would be analogous to this equation we wrote down for governing asymptotically the coupling between the metric on the base and this map into the moduli space of structures on the fiber. So here the moduli space would just be represented by a single parameter r, giving the diameter of the hose. Actually, before we go on, let's be a bit more precise, because we'll need this later. When we talk about moduli spaces, we have to be careful in various ways. So to be precise, let us consider not the full diffeomorphism group, but the subgroup of diffeomorphisms isotopic to the identity. So this is a normal subgroup, and the quotient by the full diffeomorphism group by the subgroup is what's called the mapping class group. I mean, this is originally the terminology from the case of Riemann surfaces. So then we can form what you might call the Teichmüller space of Einstein. We take all the Einstein metrics, but we divide not by all diffeomorphisms, only by these ones isotopic to the identity. So by construction, then, the discrete group, the mapping class group, which we're calling gamma, acts on this Teichmüller space, and the quotient is our moduli space. So a better way then to express what we're doing is to say that there is a flat bundle over the complement of this exceptional set in the base. The fiber is this Teichmüller space. The structure group is this discrete group gamma. And rather than a map, we should really think of this chi as being considered as a section of this bundle. But because this gamma is a discrete group, it's sort of locally essentially the same thing, but more accurate technically. Well, we talk about compact manifolds of zero Ricci curvature. The only examples of those which are known, apart from the case of flat manifolds, not very interesting, are manifolds with what are called special holonomy, which effectively means that there is some additional algebraic structure on the tangent space of the manifold, which is compatible with the Riemannian metric in that it's preserved by the parallel transport of the Levi-Civita connection. So we'll talk briefly about a well-known and very important case, that of what's called Calabi-Yau manifolds. So we have our real dimension n, which is now 2m. So these have a compatible complex structure. So they're m-dimensional complex manifolds. It is compatible algebraically compatible with the metric. So in the familiar way, those two things define a two-form, little omega. That would be just what is a Kähler manifold. The extra thing we want is a non-zero holomorphic M form, we're calling it theta on the manifold. So this collection of algebraic data reduces the structure group of the tangent bundle down to the group SUM. If we didn't have theta, we would have the unitary group U of M, which is what preserves the complex structure. Putting in this holomorphic M form reduces us to the special unitary group. So this is known by, again, by Yau's proof of the Calabi conjecture, that there are many of these things and they can be characterized actually algebrogeometrically, essentially, in terms of complex geometry. For example, if we took any complex hypersurface of the appropriate degree in projective space, so the degree should be one more than the dimension of the projective space, then we get a manifold which, it's proved, admits such a metric. And this is not a metric that one knows explicitly, that you could write down explicitly, but there is an existence proof which asserts that it exists. And if we take m equals 2, so we're looking at complex surfaces, then this goes back to the case we considered before, considering surfaces of degree 4 in three-dimensional complex projective space. So now, for such a Calabi-Yau manifold M, there's a special class of submanifolds called special Lagrangian submanifolds, and these can be defined by saying that we have first of all, they're submanifolds of half the dimension, and they're characterized by saying first they're Lagrangian, so the restriction of the two form to L vanishes, and secondly, that we take the real part of this holomorphic M form, so that's a real M form, that should also vanish on the submanifold. So there is a famous and long-standing problem or circle of questions related to a particular case of this collapsing phenomena in the case of these Calabi-Yau manifolds. This is what's called the Strominger-Yau-Zaslow conjecture, going back 30 years, it looks like. So it says that if we consider complex structures which are near to a certain limit, then the metrics collapse along a special Lagrangian torus fibration. So we're doing something similar to what we discussed before, where we were considering moving towards a singular surface with the ordinary double point singularity. But now we're considering moving towards a different kind of degeneration of the complex structures, which we won't explain in detail. But the statement is that when we do that, and we follow, well, yes, the problem is, the conjecture is, when we do that, then near to that limit, we will have a special Lagrangian torus vibration, and the passage to the limit, the sequence will collapse by collapsing the fibers of this vibration. So we have, in the setting above, we have our map from this Calabi-Yau manifold to some base, which is, the base is again half the dimension, and the non-singular fibers should be special Lagrangian tori in the manifold M. So how does our map chi work in this situation, or somewhat conjecturally? If we think of the torus as think of this stuff giving a fixed description as the quotient of Rm by the integer lattice, then the Teichmuller space, parameterizing the Euclidean structures or flat Riemannian structures on the torus, it just corresponds to the Euclidean structures on Rm, that's to say, positive definite quadratic forms on Rm. So what happens in this situation, or is expected to happen, is that the base has a flat structure, locally a flat structure, and the map to Teichmuller space is defined by taking the Hessian of a convex function on Rn, which solves the real Monge-Ampère equation. The determinant of the Hessian is equal to 1. So if we have such a convex function, its Hessian at each point is a quadratic form and is just the data required to define a point in our Teichmuller space. And indeed, one can easily check that if we define a map in this way, it does satisfy, it gives a special class of solutions of this coupled equation that we wrote down for the general case. So that's all we'll say about this well-known situation and problem. It's very important, partly because it gives a conjectural geometric explanation of mirror symmetry, in which one gets a mirror dual Calabi-Yau manifold by taking the same base and replacing the tori by dual tori. That is the general idea. So these are all very difficult things to prove. People have worked on it for many years. I should say, in the last couple of years, great progress has been made by Yang Li on proving the existence of these special Lagrangian vibrations in a wide range of cases, outside a set of small volume, because we always expect to encounter these singular fibers, which are much harder to understand exactly what happens around those. So that ends my first sort of survey part of some chain of ideas involving Riemannian geometry and specializing to these particular situations. Now I want to go on to another less well-known, less studied perhaps, special case in which we're studying manifold, 7-dimensional manifolds with the structure group determined by the exceptional Lie group G2. So this group, you can think of it as a subgroup of SO7, and it can be defined in many ways. One way is to define it as the subgroup which preserves a standard skew-symmetric cross product on R7. Well, how do we write that cross product down? That can be done in, again, a number of ways. One is to take R7 and write it as the sum of the quaternions, 4-dimensional quaternions, and a 3-dimensional piece of the imaginary quaternions. So then, to give a skew symmetric map from H plus imH times itself back to itself, we have to give a number of different components. For example, we have to give a component from the imaginary part of H times the imaginary part of H, the imaginary part of H, and so on. And then you can see that there are candidates for all such maps given by quaternion multiplication. So on the imaginary part of H, which is just R3, if you like, this is just the ordinary cross product. And then there are things, so the second map maybe is not, the second map is given by this formula in terms of quaternion multiplication. Of course, you have to fix some signs to get exactly the right cross product. You have these different pieces. To put them together, you need to choose some signs in the appropriate way. Otherwise, you get a non-compact group that doesn't lie inside SO7. So that's a sketch of how this cross product is defined, and thus we get this group G2. From the way we've defined it, though, it's not really clear that this is an interesting group. The definition appears to depend upon this decomposition of R7 into a 4-dimensional and 3-dimensional piece. But in fact, there's a lot of symmetry that is not apparent immediately from the way we've defined things. So if the symmetry, for example, all unit vectors are the same from the point of view of this cross product. G2 acts transitively on the set of unit vectors in R7. Algebraically, what we can do, we can use the standard Euclidean structure on R7 and combine that with the cross product to define a 3-form. This is phi. This is totally antisymmetric in the variables x, y, and z. So this is just the same formula what you're familiar with in the case of the cross product on R3. So a G2 manifold, we'll use this terminology for simplicity in the talk. It's a Riemannian 7 manifold with a cross product on each tangent space, which is algebraically equivalent at each point to the model above, along with the pair consisting of this cross product and the Riemannian metric, and crucially is preserved by the parallel transport. So this is a way of saying that the holonomy group of the manifold, as it's called, is contained in this exceptional group G2. And it's a fact, again, that any such a thing has Ricci curvature equal to 0. And then there are various things we can do with the differential geometry of the situation. The cross product, just the same way as we did at the top of the screen, defines a closed 3-form on the manifold. And we have a distinguished class of submanifolds, called, these are 4-dimensional submanifolds, called co-associative submanifolds, which are characterized by the fact that the restriction of this 3-form should vanish. So these are very analogous to the special Lagrangian submanifolds we were discussing before. The deformation theory of these manifolds is also well understood, of these 7 manifolds, at least in the compact case. If we have a compact manifold with one of these structures, then the small deformations of the structure, modulo diffeomorphism, correspond exactly to deformations of the cohomology class of the 3-form in the 3-dimensional real cohomology of the manifold. So if you like, the moduli space of these structures has dimension, in particular has dimension equal to the 3rd Betti number of the manifold. So the direction we're going then in this section is to ask what are the possible collapse limits of sequences of G2 structures. So in our general picture, if the base has got dimension 7 minus k, the generic fiber should be a k-dimensional manifold, which should support metrics with zero Ricci curvature. So apart from the case k equals 6, where we'll get these Calabi-Yau threefolds again, and the case where we have flat fibers, tori, say, like as in the previous discussion, the only possibility, at least it's known, is that k is 4, and the fibers are little K3 surfaces, that's to say, Calabi-Yau manifolds of complex dimension 2, such as, for example, the surfaces of degree 4 in CP3 we discussed before. So let's consider that situation where we have a map of fibration above 7 manifold over a 3-dimensional base, where the generic fibers are diffeomorphic to the K3 manifold. And we also suppose, and there are good reasons for doing this, that the fibers are co-associative submanifolds. Again, analogous to the special Lagrangian fibrations in the previous case. And we suppose that the exceptional set delta in the base is one-dimensional, a link, a union of embedded circles. So we're supposing all that. Why? It's known from a construction of Kovarev from 20 years ago, and more recent work of others, in particular recent work of Engelbert, that many such examples of this picture exist. But one has not just sort of, well, isolated examples, but whole families, because we can deform the structure, at least a small amount, by, that corresponds to deforming the cohomology class in the 3-dimensional cohomology. But then there is a preferred class in the 3-dimensional cohomology given by the lift of the fundamental class of the base. And the picture one expects is that as the cohomology class of our 3 form approaches that lift of the fundamental class of the base, then that will force us into this situation where the fibers of this fibration collapse. So we can sort of investigate our general picture in this situation. The tight Muller space of the K3 manifold is completely understood through what's called a Toredi theorem. So this is analogous to the classical Toredi theorem, which applies in the case of Riemann surfaces. Let's just explain that. So, as we said, for a Calabi-Yau manifold of m complex dimensions, the structure group is actually SUM. When m is 2, we have the group SU2, which can be identified with the group of uniac quaternions. So we can also think of a Calabi-Yau surface, or 2 complex dimensions, 4 real dimensions, as having a quaternionic structure on its tangent space. It is, in a sense, a one-dimensional quaternionic manifold. And then we have a triple of closed 2 forms, expressed in the way we had before. We have the Kähler form, omega, and then we have the real and imaginary parts of the holomorphic form. So in this case, these are all 2 forms, and they're all on the same, although it doesn't appear it this way, they're all the same standing. There's another complex structure, for example, where omega 2 is the Kähler form, or omega 3. So these 3 two forms correspond to a triple of complex structures, IJK, or more invariantly, you could say there's a whole two spheres worth of complex structures. And indeed, if we take such a structure, then the product of X with a flat R3, we think of R3 as the imaginary quaternions, does have a G2 structure we can write down using the quaternions on its structure on the tangent bundle of X. Essentially, we apply the recipe we used for the cross product to define a cross product on the tangent spaces of this product. So what should the equation be, giving the slow evolution, as it were, of the structure on the fiber over the base? We can understand that, or explain that, in terms of actually topology of the situation. If we look at the two-dimensional cohomology of our K3 manifold, that is a space of dimension 22, and it has a quadratic form given by the cut product, which has got signature 319, 3 positive directions, and 19 negative ones. So if we have one of these Calabi-Yau structures, then it defines a three-dimensional subspace given by the span of these 3 two forms that we wrote down. And this is a positive subspace with respect to this quadratic form in the cohomology. Conversely, if you take any maximal positive subspace, then it's shown by a lot of work and contributions of many people that there is a corresponding Calabi-Yau structure, unique up to diffeomorphism. So actually that's slightly imprecise. To make that happen, we need to allow also these objects with orbifold singularities, which corresponds to a special class of positive subspaces. But we won't go into that for the purpose of this talk. So slightly imprecisely, the conclusion is that our type Muller set space, in this case, is the set of positive three-dimensional subspaces in R319. So locally, remember what we have is a map from, at least from some suitable open set, there's a missing B here, a suitable open set U, the complement of delta, into this type Muller space. But what is the equation in this situation which should characterize this map? What it is, requirement is that this map is the Gauss map of an embedding of U into this space with its indefinite quadratic form. So if we have such an embedding of U into R319, then the Gauss map assigns to each point of U the tangent space of the tangent space of the image of the corresponding point, which is a three-dimensional subspace, so a point of this Grassmannian. But we want the image to be what's called a maximal submanifold of R319, which is something we will now review. So a maximal submanifold in an indefinite space is just an analog of a minimal submanifold in a Euclidean space. It's to say, first of all, we require that the tangent spaces are all maximal positive subspaces with respect to the quadratic form. And then we require that the submanifold satisfies the Euler-Lagrange equation associated to the volume functional. We can find the volume functional in this situation in exactly the same way as in the Euclidean case, and therefore it produces Euler-Lagrange equations. So to see that explicitly, if we consider the case where we have one negative dimension and we consider manifolds that can be written as graphs of a function, then this is the maximal submanifold equation for a graph. And it's the same as the minimal submanifold equation for graphs, except that we change the sign here. In the minimal case, you'd have a plus here, which corresponds to the fact that in order to satisfy this algebraic condition on the positivity, we need the derivative of u to have length less than 1. This is a second order nonlinear PDE, sort of quasi-linear equation of Laplace type. The leading order term is, roughly speaking, the Laplace equation, or a variant of the Laplace equation for the function u. So the asymptotic data, in sum, that we expect from this approach to the collapse limit consists of a 3-manifold, a link in the 3-manifold, a flat bundle over the complement of this link with fiber this indefinite space R319, and a section of the bundle of positive 3 planes in E, either bundle whose at each point we take the positive 3 planes in the fiber of E at that point, but which satisfies a partial differential equation, which can be expressed by saying locally it's the Gauss map of a maximal submanifold parameterized by a section of E, a section of this vector bundle. Well, that's all away from delta. What happens when we approach delta? This is perhaps the most interesting part of, well, the most interesting part and the part where all the difficulty in understanding things occurs. So the flat bundle, for the kind of singularities that we want to consider, which I'm not going to talk about in detail, but it has the property, it has non-trivial holonomy going around the small loop around one of the components of L. So when we're considering these local sections iota, away from delta, they're given by maps or vector value functions. But we can't do that around a point of delta. Delta is now this link L. The basic model that we require is that it looks like essentially like a surface with a branch point. So this transverse to L in 2 dimensions, and for simplicity taking 1 negative dimension rather than 19 dimensions. We want our submanifold to look like the graph of this 2-valued function, the real part of z to the 3/2, as z tends to 0. So in classical minimal surface theory, these kind of branch points are much studied in the case when we're considering 2-dimensional minimal submanifolds. Here it's different because we're considering things that look like that transverse to this set L, but have higher dimensional singular sets. So that brings me on, taking the time, I have 8 minutes left, to the last part, where you say this, I've tried to outline how following this line of thought, studying this particular version of this general collapsing question, leads to these solutions of, in that case, a nonlinear elliptic PV, but they have this essential value, property of being 2-valued solutions as we go near the singular set. So that fits into a whole class of problems and questions that have arisen in different parts of differential geometry over the past 10 years or so. These include questions in gauge theory, questions initiated by Taubes, and things studied by Taubes, and also in study of calibrated submanifolds. So I'm to talk very briefly in the last 5 minutes about some of the analytical features of these questions. So the simplest setup is consider a Riemannian manifold with the fixed metric, a codimension 2 submanifold, and a flat real line bundle on the complement of that submanifold, having being non-trivial, so having holonomy -1 as we go around small loops around sigma. So we have a Laplace operator then acting on sections of this flat bundle. So locally, away from sigma, it's identical to the ordinary Laplace operator, but we have interesting new phenomena due to this singularity at sigma. But let's write r for the distance to sigma, I'm going to say. So let's just, to explain the main thing, let's consider this model problem of solving an inhomogeneous equation. So we take some prescribed source, rho, which for simplicity, let's say it's compactly supported away from sigma. We want to solve the equation delta of S is rho. So if we work in a class of sections S, which is suitably large, which are, roughly speaking, allowed to behave like order r to the 1/2 near to sigma, this is something that's easy to understand. You can show quite a straightforward way that is a unique solution to this equation. The basic thing is that these things have derivative in L2, so one can, for example, use the ordinary Hilbert-Straits methods to produce a solution. And in fact, I can go on, the asymptotic behavior can be understood of this thing around sigma. We're supposing rho is 0 near sigma, can be understood. They look like essentially the real part of z to the 1/2 multiplied by a scalar factor depending on the point of sigma. So here, z is a complex normal coordinate, local coordinate in the normal direction, and t is a coordinate along sigma. But these are not the things that we want in the applications that I have in mind. So in particular, I mean, the nonlinear version that we encountered in section 2, we're looking at a nonlinear equation, but it's sort of Laplace type, roughly speaking. And we definitely don't want these solutions which behave like order r to the 1/2. Those wouldn't make any sense in our problem. What one needs is what we might call briefly order r to the 3/2 solutions, where this coefficient alpha is identically 0. And those have got asymptotics given in a similar way, but with a power 3/2, which is just what one needs geometrically for all these applications. So the feature is that typically, if you fix sigma, you will not find these, because you solve the problem, and the space you solve it in are things which are order r to the 1/2. So in order to find these things, you can't fix sigma, you have to deform it. So the problem and the analysis is closely analogous to free boundary value problems, where you take, say, some domain and you look for, say, a harmonic function or something in the domain, you impose both Neumann and Dirichlet boundary value problems. So you don't expect to be able to solve that with a fixed boundary, but you have to vary the boundary to solve it. So this is the same situation schematically, except that rather than a codimension 1 boundary, we have this codimension 2 singular set. So, for example, one can show, I can understand this sort of deformation version of this setup. Supposing we have one order r to 3/2 solution with some singular set for a given rho naught. Now we deform rho naught slightly, then one can show that there is a unique small deformation of the singular set with a corresponding solution of the desired kind. But the underlying reason why you could do this is just the base elementary formula. The derivative of z to the 3/2 is a multiple of z to the 1/2. So roughly speaking, when you deform sigma, the z to the 3/2 term, when you bring in a term involving its derivative, which gives this z to the 1/2 term, which you can use the counterbalance, the z to the 1/2 term coming from the linear theory. So it's not hard to understand, in a sense, why this should be true, but the proof is not so easy, because when you write it down, you find that you encounter a problem of loss of derivatives in the natural way of setting it up. So although the sort of general shape of the problem is something you approach an implicit function theorem, you have to use a more sophisticated kind of implicit function theorem involving the Nash-Moser theory. So that's one aspect of the interesting analysis, which interesting kind of analysis geometry questions, which appears when one's studying this particular situation of this general collapsing phenomena. Also interacts, as we said, with many other questions in contemporary differential geometry, and is an area which I think will see many developments in the years to come. So that's, I finished. Thank you very much for listening.
Okay, Professor Donaldson, thank you very much for your talk. Can you hear me?
Nope.
Give me a second, please.
Okay. Thank you very much for your nice talk, for your interesting talk. We now are open for questions. I don't know if someone have a question in the chat. In the meantime, I wanted to ask something. For example, for spin 7 manifolds, is there something analogous to these multi-valued functions, or in that setting, how can work analogously to the approach of
Yes, that is an
multi-valued functions?
That is an interesting question. A good question. That one can write down a theory, as it were, in the spin 7 case, but there are the drawback is that there are not so many potential examples at the moment. So one can write down some interesting but slightly less familiar kinds of equations, but all within the same sort of scheme. But it's maybe there's less motivation because it's hard to find examples, but it's quite likely something that will develop in the future.
Okay, nice.
When
And another question.
Yep.
Okay, and just I have another question, if I may. Always when you have this situation in which you have a family or a sequence of G2 structures collapsing, you always will have the multi-valued function, and they are always harmonic.
Not exactly. No, not really. I mean, they satisfy this sort of nonlinear variant of the Laplace equation, given by this maximal submanifold equations. So it's somewhat more complicated to set up, but many of the same phenomena that appear for the Laplace equation, the problem for the Laplace operator that I discussed, appear for this more complicated nonlinear equation.
Oh, okay. Okay, Professor Donaldson, maybe in the chat, if someone have some question, let me see in the YouTube chat. Okay. No more questions. So if I may, a last question for you. I don't know if there is something like a manifold or like a setting like that, but considering symmetries, for example, in manifolds with cohomogeneity one manifold, you have a family of principal orbits in some way collapsing, or not necessarily collapsing, but tending to a singular orbit that can be Lagrangian or minimal. I don't know if adding or if there is an example of a setting of G2 structure, but when you have more symmetries, maybe an action of cohomogeneity one or something like that. It's just a curiosity.
Let me try to think. For actual compact G2 manifolds, they won't have, by the basic theory, they cannot have any killing fields. I mean, if they're genuine G2 manifolds. Like they're not a product, say, of a circle with something else. So symmetry doesn't help in an obvious way there. But for many of the associated questions, in particular in the case of, say, point singularities, where you get, you want to describe cones on a six-dimensional manifold of a particular kind, then symmetry techniques are very valuable. They were used by Foscolo and Haskins, for example, to construct unexpected new examples of these things. Exactly, so with cohomogeneity one techniques and reduced to ODEs. So in a slightly roundabout way, these symmetry techniques are important. Yeah.
Okay, Professor. Andrea, you can mute yourself. You want to make a question, please?
Yes, hello, Professor Donaldson. Yeah, I would like to ask you something.
Mm-hmm.
In the second part, you described these exceptional Lie groups through this cross product on R7. So you can just have this cross product on R3 and R7, right? And do you think this algebraic characterization could also provide a useful framework for studying geometric analysis, for example, diffusion equations, because the Laplacian transfers to this Brownian motion? Because I am in this area, not in your area. That's why I wanted to ask you this.
I didn't quite follow the question. So we're looking at the cross product.
Yes, and then does it make sense to use this algebraic characterization to study this geometric analysis directly on these G2 manifolds?
No, I'm not quite sure. It does. One can think of it as giving a sort of a different way of a special way of representing the Dirac operator, similar to the way that you have in 3 dimensions. You have the curl operator. So that is not the curl operator taking vector fields to vector fields. That is sort of a special feature of 3 dimensions, roughly speaking. It's not something which works in general. So in a way, this cross product of 7 dimensions does give something a bit like that. But I'm not sure if that is exactly answering your question. But that, yeah.
Okay, Professor, thank you.
Okay, so thank you again, Professor Donaldson, for sharing with us that amazing talk. And thank you for being here. We're very happy you accept our invitation to this Congress.
Yeah. Well, thank you. I'm enjoying it. Thank you for asking me. Yeah. Okay.
Yeah.
Okay.
Bye-bye.
I'll sign off. Put my screen off.
Okay, so next talk and our closing talk will be in charge of Professor Maria Jose Pacifico, but it will start in about, we're having some troubles with technical support, but we're dealing with it. So thank you for your patience.
Hello, everyone. We are having some technical difficulties, but we are solving this issue at the moment. So please stay here for the talk of Professor Maria Jose Pacifico. And also in 1 hour, we will have our closing ICMAM prize ceremony. So please stay here with us. See you soon. Hello, Professor Pacifico.
I'm not understanding because I have just the program for the meeting. The last policy already finished because YouTube it suddenly stopped.
Yes, but now
I
you're
hear
here. Thank you very much. We can hear you,
Okay.
yes. See you.
We apologize for the
Okay.
inconvenience, Professor Pacifico, but now you're here, so welcome and please apologize.
Okay, now I can take my talk. Is this because I have just the program for the meeting. Yes. The last policy already finished because YouTube it suddenly stopped. Yeah.
Yes, but now
I
you're
hear
here. Thank you very much. We can hear you,
Okay.
yes. See you.
We apologize for the inconvenience, Professor Pacifico, but now you're here, so welcome and please apologize.
Okay, now I can take my talk. Is this because I have just the program for the meeting.
Professor,
Yes, the policy already
I
finished
think you
because
have,
YouTube it suddenly
maybe
stopped.
you can,
I will see.
you can close the window of the YouTube, of the YouTube streaming, please. And we can stay just in here.
I have just the program for the meeting. Are you here, me? Vocês me ouvem direitinho?
Sim, professora, estou te ouvindo. Só que acho que tem. Você fechou a janela do YouTube? É que estamos ouvindo um retorno.
Não escuto você.
Não? Não consegui me ouvir? We can stay just
Assim.
here.
Não. Uhum. Are you here, me? Vocês me ouvem direitinho?
Professora, é que acho que você tem a janela de YouTube aberta. Então vamos ter que pedir para você, por favor, fechar.
Ok. Peraí.
Ok? Agora
Não
sim.
escuto você.
Não. Não consegui me ouvir?
Ok. I closed the...
Perfect.
Okay.
Now we are fine.
Okay. I closed the YouTube. Okay. Now I can understand what's going on. Okay.
Okay, Professor, now we are sorry for the delay. I'm going to present your talk. Just a little second. I want to apologize to you and all the participants for these technical problems and for this delay in the program. But now it's a great pleasure for me to introduce Professor Maria José Pacifico, one of the leading figures in dynamical systems in Brazil and Latin America. She's a full professor at the Institute of Mathematics of the Federal University of Rio de Janeiro. Over the course of her career, she has made important contributions to the study of flows with singularities, singular hyperbolicity, and Lorentz-like dynamics. Her work has lasting influence on the development of the field. Equally important has been her dedication to the training of young mathematicians and to strengthening the dynamical system community in Brazil through supervision, collaboration, and the organization of scientific activities. Today, Professor Pacifico will present her talk entitled An Ergodic Spectral Decomposition for Singular Star Flows. Professor Pacifico, thank you again for being here with us. Please go ahead.
Okay, many thanks for the invitation and many thanks for the introduction. And then today I will talk about the spectral decomposition conjecture for star flows. And the motivation for this is following a guiding principle in smooth dynamics, which is to understand a complete complicated dynamical system by decomposing it into simpler invariant pieces. And for uniformly hyperbolic system, this principle is realized by two fundamental achievements: Ismai's spectral decomposition and Bowen's thermodynamic formalism. One of the milestones of modern dynamics is the following theorem due to Steve Ismay, which says that if you have a diffeomorphism defined on the compact manifold, which is axiom A, then the non-ordered set can be decomposed in a disjoint union of compact invariant hyperbolic and transitive and local sets, this lambda I. What means axiom A is just that diffeomorphism is hyperbolic, sense that in the tangent bound you have decomposition that such that the derivative, the deposition in the tangent bundle in subspace, complex subspace, that the derivative contracts uniformly the vectors in one of the subbundles, and the derivative expands uniformly vectors in the other bundle. And the non-ordered set is just the set that we are interested in knowing, because it are sets that if you take a point in the non-ordered set, the point, the orbit or the trajectory of this point does not return to this point. And the same theorem holds for non-singular flows, that is, flows such that they never vanish. For any x, the flow doesn't vanish there. And the Bowen ergodic picture for this kind of flow says that the hyperbolicity has remarkable ergodic consequences. For it, in other words, that for each basic set, there is a unique equilibrium state, a unique measure of maximal entropy, specification explaining all these terms that appears here. Okay, and so the question is, what survives if we are dealing with flows presenting singularities? Flows with singularities are not uniformly hyperbolic, typically not stable, and not covered by Bowen's theory. So, the main question is, can one recover a Bowen-type thermodynamic formalism for singular flows? Singular flows means that the flow has singularity, okay? And our answer is yes. Our main ergodic result, it's two theorems together with Jiagang-Yang and Fang-Yang. We prove that there exists a C1 open and dense set U contained in the set of the C1 star vector fields on the manifold with a positive topological range, such that every flow in this set has only finitely many ergodic measures of maximal entropy. A continuous holder the C1 open and dense set contained in the set of C1 star vector fields with a positive topological entropy, such that every X in the set has only finitely many equilibrium states, provided that the value of the potential at any singularity is less than the pressure in the whole space. Okay. Okay. And let me just tell you the notions of hyperbolicity. Given a C1 vector field on compact manifold M, and denotes the singularities of X as this point is the set of points in the manifold is such that the vector field vanishes at the point. Uniform hyperbolicity means that the tangent bundle decomposed in a direct sum of this sub-bundle, it's called the stable bundle, plus this is the bundle tangent to the flow, and the other sub-bundle is called the unstable bundle. And here, the derivative of the flow contracts uniformly vectors in this sub-bundle. Here, the derivative expands uniformly vectors in this bundle here. Moreover, this decomposition is uniform in the sense that if you have a sequence converging to some other point, the decomposition also converges to the decomposition at the limit point. And another section is the sectional hyperbolicity that we just weaker this notion above. That means that you have at the tangent bundle, you have ES, which is a uniform bundle in the sense that the derivative contract uniformly vectors in this sub-bundle. And another complementary subspace that we call FCU, where what happens is that for every subspace, two-dimensional subspace contained in this space here, the derivative contracts volume. And the sectional hyperbolicity is equivalent to uniform hyperbolicity when you don't have singularities. That's the point. And okay, why to give it the answer or to prove these theorems is difficult to achieve the result? Because when you have a sectional hyperbolicity, you have dominated splitting in the tangent bundle. And on the other side, if you have a multisingular hyperbolicity, which is an even weaker notion of sectional hyperbolicity, the tangent, you have this decomposition in the non-bundle, tangent bundle. The singularities for sectional hyperbolicity always the same index, and for multisingular hyperbolic flows, they may have different indices. In this case, the dimension of the stable singularity, and the kind of symmetry sectional hyperbolic flows, and very weak for multisingular hyperbolic flows. And the structure is better understood for the sectional hyperbolic case and mostly unknown for singular flows. The multisingular case is much, much weaker than the class hyperbolicity. And the motivating example for us Lorentz system. Indeed, in 1963, Lorentz published his famous paper, Deterministic Non-Periodic Flow, in the Atmospheric Journal. in which he studied the following system of ODS as a model for thermal convection. You see that these equations nowadays are known as Lorentz equation. And the three equations are quite simple, are polynomial, 2-degree polynomial. But at that time, Lorentz could not solve explicitly this flow. You know that indeed zero, it exists to see that zero is a singularity because it vanishes the of this. And okay, then the predicability, does the flap of a butterfly wings in Brazil set off a tornado in Israel? I don't know. That was the butterfly effect that Lorentz coined the term butterfly effect based on the shape of the attractor and the meaning of independency of the trajectories in relation to the initial conditions. The Lorentz attractor shows that singular flows may exhibit robust chaotic behavior. And this motivated the search for an appropriate notion of hyperbolicity beyond the classical one. What is the meaning this? The meaning is that even it appears so chaotic, no? But this is robust. In which sense? You can take this equation, this vector field here, you can change a little bit these parameters. This is the parameters like this one are nowadays are known as the classical parameters. But if you perturb, you have the same kind of shape. You still have something similar to a butterfly. And the meaning of this and the way the orbit or the trajectory goes around the singularity is completely random. You cannot say, okay, if it's now it's in one wing, then it will go, the next will go to the other one. No, it's completely random. And this fact happened for every perturbed the equations. And that was quite amazing because how to characterize this kind of flows. Because certainly this flow is not uniform hyperbolic because the singularity just any splitting that you take in the tangent bundle just degenerates the singularity, disappears, okay? So, and in this direction, the next step is to define what's called the star flow. The condition is that the vector field has the star property if every nearby vector field has only hyperbolic critical elements. Star flows are often regarded as the natural analog of axioma A systems. And the singular star flows extend this analogy to axioma A systems with singularities. You see that the Lorentz flow is a singular star flow because the singularity of the Lorentz flow is hyperbolic, and if you perturb a little bit, it is the perturbed singularity is also hyperbolic, and so is the more significant. How you say this is more significant example of a star flow, singular star flow. And why star flows? Why? You have the stability conjecture by Pallas-Ismail that say that structural stability is equivalent to hyperbolicity. And the stability conjecture naturally leads to star systems because a structural stability implies star property. And the known results on these directions are for diffeomorphisms. This was solved by Ismail, Franks, De Mello, Liao, Magnan, and for non-singular star flows was solved by Hayashi, Gunn, and Wen, but for singular star flows, not yet. Also, then let's unpacking the history of this kind of story. The uniform hyperbolicity plus transversality implies structural stability. And the stability conjecture has two steps. Step one is that structural stability implies the star condition. Every periodic orbit of every nearby system is hyperbolic, and that was proved, as I said before, by De Mello, Bromes, and Franks. Now, and the second step is that to prove that the converse, no, that a star condition implies structural stability. For diffuse, star condition implies uniform hyperbolicity. This was proved by Liao and Magnier. And for flows, when you don't have singularity by Hayashi, Gunn, Wen, and with singularities, the same index, you have sectional hyperbolicity by Shi, Gunn, and Wen, and the different ends multisingular hyperbolicity that was by Bonatti and Dalus. Why axioma A system with singularities? Axioma A is where Ismail's spectral decomposition works, thanks to the uniform hyperbolicity, no singularities. Near a singularity, sigma, the hyperbolicity genuinely degenerates. This is a real obstruction, not just a technical one. And the 10 box there above tells the story of how hyperbolicity was generalized to handle this, while keeping the same structure wholly axioma A played. And Lorentz forced the classical hyperbolicity was too restrictive. Sectional hyperbolicity generalizes this to Lorentz-like attractors, same index. Any multisingular hyperbolicity covers different indices, density and the genetic case. Then Ismail, each notion above replaces Ismail's uniform hyperbolicity in exactly the whole of guaranteeing controlled splitting and robustness, opening the door to spectral decomposition and the thermodynamic formalism, which is the rest of the talk. Then the spectral conjecture for star flows. The conjecture is every C1 star flow admits only finitely many non-trivial chain recurrency classes, which is equivalent to the conjecture that every chain recurrency class should be the homoclinic class of a hyperbolic periodic orbit. This is the natural singular counterpart of Ismail's theorem. Okay, but our point of view is rather than proving the topological conjecture directly, this is as the topological conjecture for the spectral decomposition for star flows, okay? And our point of view is that rather than proving the topological conjecture directly, we first establish its ergodic counterpart. That is, we first prove the ergodic version. This turns out to be accessible through thermodynamic formalism. Then the theorem is given a continuous Holder potential, phi. There exists a C1 open dense set contained in the set of C1 singular star flows with topological entropy positive, such that every X in the set has only finitely many equilibrium states, provided that the phi applied to any singularity is strictly less than the pressure of the whole space. And this leads naturally a Bohm type theory for multisingular hyperbolic classes, which is the technical obstacle. For uniform hyperbolic systems, thermodynamic formalism relies on three fundamental ingredients: invariant stable and unstable foliations, expansiveness, specification. For multisingular hyperbolic flows, none of this is available in general. And the main challenge is recover enough hyperbolic structure to rebuild thermodynamic formalism. Then the general strategy is you have a multisingular hyperbolist, then try to use Liao geometry, and then get good orbit segments, and in these good orbit segments, you prove Bohm property and specification, and then use what is called improved Klimen-Haga-Thompson criterion, and to get the finite number of equilibrium states. I will try to give an idea of this strategy, okay? Well, the first ingredient. The first ingredient is called the Liao geometry. Because a classical local product structure is no longer available. Product structure means that if the stable and unstable manifold, they intercept in one point, this point of the intersection should be nearby the original one. And instead, since this is available, we work with scaled neighborhoods that compare the flow with the velocity of the flow on each point. We use fake invariant foliations, reparameterized shadowing. These tools allow us to recover local hyperbolic geometry even near singularities. Good and bad segments. The point is that the orbit segments we decompose in two families, GB and GS. Like this, you have this is just one, but it's like a bunch of segments of orbits, and you just decompose it on the sets. GB is the central one, and the GB, like the B, contains the good orbit segments, and select the true hyperbolic behavior and control the recurrence. On this collection, we prove Bohm property and specification. And GS contains the remaining orbit segments. The key point is to show that they carry strictly smaller pressure excuse me, and therefore do not contribute to equilibrium states. We are trying to use here the Boeing strategy. Boeing strategy, since in the beginning, he used that Boeing property that I will explain, specification, expansiveness. These three things implies existence of equilibrium states. We are just trying to follow Boeing strategy, but it's not enough. We have to use what's called the Klimenhaga, improve the Klimenhaga-Thompson strategy or criterion, which was exactly this. To decompose the orbit segments in this kind of families, the good ones and the other ones that you can, that they carry strictly smaller pressure and therefore do not contribute to equilibrium states. And the good orbit segments, the collection is constructed from points with infinitely many slow recurrent place times. These points exhibit a persistent hyperbolistic, controlled recurrency away from singularities, uniform local geometry. And this is precisely the setting where Liao geometry can be fully exploited. This place times, I times, okay, you don't have uniform hyperbolist, but please prove that if you can find infinitely many points or times such that the orbit through this point behaves like if it were hyperbolic. And slow recurrent, because this is not enough to prove, you have to define another type of place time that we call the slow recurrent place time, is just to deal with the segments that pass nearby a singularity. And then to establish the Boeing property, we first identify good orbit segments through infinite slow recurrent place time, which provide persistent hyperbolic behavior along the orbit. You have, this is represented is a ball, a Boeing ball that you follow the the orbit of points in this neighborhood. They are nearby till some iterated, and we just prove this, that the informal proposition to this point is that if xt is a good orbit segment and y belongs to its Boeing ball, then y is scaled shadowed by the orbit of x. This means that the distance between the phi s of x and the phi s of the orbits, point by point iterator, is comparable with the velocity of the flow at the point for every s in this segment of orbit. Hence, closeness in Boeing balls automatically enters the scaled hyperbolic geometry of Liao. Okay. How do we win? The usual place times are not enough once the orbit comes closer to a singularity. We need a new kind of place time, and the slow recurrency hyperbolic time. For a good orbit segment, xt, this represents a segment and not only a point. And for any s in this interval, the segment, when you fall, you will evolve by time, can only spend a small portion of its time inside the neighborhood of the singularity. This is the singularity, and this is represent a neighborhood where you lose the hyperbolicity, because here the flow vanishes and then you are losing hyperbolicity nearby here. And then what you do, we're able to find this kind of slow please time that this kind of, when the amount of time that it spends inside this neighborhood is small compared with the time that it spends outside W till the next entrance in this neighborhood. You have bad segments, but the other segments have enough hyperbolicity to cover what is lost in this neighborhood. And with this, it just can you prove the Bohm property, okay? And there is the specification property. Specification property is like this. You have one segment of orbit here. You have an orbital, and what you get that the orbit of a nearby point is shadowed, but in one piece here, and then it goes outside, but then it comes nearby again, and then go outside, and then come returning to be nearby the orbit of the point. The starting point is the easiest, the existence of infinite slow recurrent place times, which detected points with persistent hyperbolic behavior. Let me just... And the informal proposition is that there exists a large compact set of good points detectable by invariant measures whose local invariant manifolds intersect transversally those of a fixed hyperbolic periodic orbit at a uniform scale. These transversal intersections provide the mechanism needed to glue orbit segments and recover specification. You see that all this, what we are, if you put everything together, you have that Bohm property implies bounded distortion. Specification, you can orbit gluing. And together they allow us to apply this criterion, the Klimen-Haga-Thompson improved criterion, and obtain a finite number of equilibrium states. What just in a few words, what is this? Because Klimen-Haga-Thompson, they give you a criterion that you could follow Bohm strategy to get equilibrium states that was obtained for diffeomorphisms in the beginning. And the Klimen-Haga-Thompson placed this for not only for diffeomorphisms, different improved Bohm strategy. But the Klimen-Haga-Thompson criterion, unfortunately, does not fit for us because of the singularity. Then we had to work a little bit more just to adapt this criterion to our setting. And what is this? In a few words, means that you just work in such a way that you can follow the Bohm initial strategy to get equilibrium state. In other words, you have to prove expansiveness, specification, and Bohm property. and you adapt it in the setting where you are working. This is the point. And from one class to all star flows, okay, each isolated multisingular hyperbolic class admits a unique equilibrium state. This was proved by Courvoisier and Bouzy. And combining this with the ergodic spectral decomposition, we have only finitely many equilibrium states for C1 open and dense star flows. In particular, finitely many measures of maximal entropy. And back to the spectral decomposition conjecture, the topological conjecture remains open. Our result establishes its ergodic counterpart. Ergodic decomposition is proved. But this brings us one step closer to the original spectral decomposition conjecture. And indeed, the ergodic result already yields a partial topological consequence that I will state now, and has a strong topological consequence, the ergodic spectral decomposition is the corollary that this says that for a C1 open on the set of star flows, for every constant, positive constant, there exist only finitely many chain recurrence classes with topological entropy bigger than C. Moreover, each such a class is a homoclinic class of hyperbolic periodic orbit, supports at most one local measure of maximal entropy. Okay. And a partial topological you have this a dichotomy that with the same co-authors, Jiagang Yang and Fan Yang, that there is a residual set of C1 star flows such that for every X in the set and every non-trivial chain recurrency class, C of X, we have that if the topological entropy in this class is bigger than 0, then this contains some periodic point P and is an isolated homoclinic class. And if the topological entropy of the flow in this class is 0, then C is sectional hyperbolic, either for X or minus X, and it contains no periodic orbits. And in this case, every ergodic invariant measure with support contained in C must satisfy that mu is the Dirac measure at the singularity, on each singularity, on some singularity in the class. Okay, so what is one remaining obstacle is that our result reduces the topological spectral decomposition conjecture to a single question. That for C1 open and dense star flows, every non-trivial chain recurrency class has positive topological entropy because of this dichotomy, no? And if true, immediately implies the topological spectral decomposition conjecture. Is this what we would like to prove? Not now, but in the next years, I don't know, in the future. And then my co-authors on this is Jiagang Yang and Young. And the reference for this are these works here that we started quite recently, from the year 2000 until now. And okay, and this is, I will stop here. Thank you very much for your attention.
Thank you, Professora Pacifico. Very nice talk. We have time for some questions. In the chat, we have a question. Is there an analog decomposition result for non-compact manifolds?
I lost the, oh my God, okay.
Okay, let me repeat the question. Can I? The first question is there an analog
You know that
decomposition result
I
for
don't know, I
non-compact
am,
manifolds?
what, okay. I stopped the convert, okay.
You
will
want to
stop,
stop sharing?
okay, now I have, okay. Now I am here, what?
Okay, Professor. Thank you for your very nice presentation again. We have some questions in the chat, so I am going to the first question. Is there an analog decomposition result for non-compact manifolds?
Sorry, oh, what is the question? You know, I'm not seeing my slide. No.
Let me see.
I don't know what happened. Let me.
You're sharing your full screen.
Is here or no? No.
Yes, now we are seeing, but it is not in full screen. No, it's behind that window. Yes, okay. Perfect.
Okay. And then what was the question? I don't know. No,
Yes,
unfortunately, all this is quite technical. If I go through the proof, I would never finish because it's quite complicated. I try just to pass the idea that to work, what we are following since the beginning is just the Boeing principle. To prove since the beginning that you have some responsiveness, specification, a Boeing property, and then you can prove existence of equilibrium states. That was the main idea behind all the problems here. How to adapt to this. And then once Klimenhagen Thompson adapted for some setting that they were interested, and then we adapted this setting just to recover specifics, Boeing property and specification in our setting. It's more the final message is this, that we have to work just to recover completely now the idea, the Boyne's idea to the existence of equilibrium states. Okay.
Okay, we have some other questions. Professor Wolfgang Bock. I don't know if this could one hope to prove full spectral decomposition by showing that every zero entropy multisingular hyperbolic class reduces to a finite configuration of singularities?
No. Unfortunately, you have to prove that exactly that in this setting it cannot have entropy zero. A recurrent class cannot have entropy zero. It's just this. What is the order? Is this, sorry, this dichotomy, that in this case doesn't exist. In another way, that if you have a C1 star flow, then and you have a non-trivial chain recurrent class, then the topological entropy has to be positive. This is what one has to prove to achieve the topological spectral decomposition. No? What we have is just the ergodic one, in the sense, meaning that we have a finite many equilibrium states, no? Recurrent classes with finite many equilibrium states. That's the theorem. The theorem is I am cheating a little bit, because what I talk most of the time not about the multisingular hyperbolic. I talk mostly about the sectional hyperbolic flows. Why? The approach here is much more complicated, in the sense that you don't have any geometry. You may not have any singularity. You don't have a tangent bundle to deal with. You don't know how to start. You know, then it's much more subtle. But we succeeded to work on this, and okay, you have much more work to set everything, and again, the difficulty is how to adapt and generalize the Bowen approach to get the finite number of equilibrium states. This is, for this set here, multisingular hyperbolic flows is much more complicated.
Okay, we have one last question. Under what additional assumptions would be the number of mixtures with maximal entropy be locally constant under C1 perturbations?
This I don't know. What I know is that what we know locally constant. By now, I don't know how to answer this correctly. Sorry.
Okay, perfect. No, thank you. And if I may make a question, I would like to ask, is there any bound on the number of ergodic measures of maximal entropy in terms, for example, of the number of singularities or something like that?
No. We didn't stabilize the. I don't know. It's just a finite number, but I don't know if it's related to the number of singularities or not of the flow. By now, I don't know how to answer this.
Okay, Professor Pacifico, we have some messages. Julio Delgado says thank you so much for the talk. Professor Wolfenbolt says thank you, and I say thank you too, because that interesting talk. It is a good way to close this conference. And now I invite you all to stay to the closing ceremony. We are going to announce our ICMAM Prize 2026, and I'm going to pass the word to.
Sorry, Brian. I stay on the Zoom, or I go through the.
On the Zoom, Professor, please.
No, okay.
On the Zoom, over here, please.
Okay.
Thank you. So the one, I'm going to pass the word for you, and you are going to chair this closing session. Please. Duan, are you there? Okay, sorry. We have a little delay again.
Okay, thank you very much. Thank you to all the participants that has been following the scientific program. Just to confirm, we have with us Professor Tatiana Toro, right? Just for practical things, let's see if Professor Toro can unmute herself.
I'm here.
Very good. Good. So, Professor Joaquin Toff, you can try to unmute yourself to see if everything works well. Professor Toff, can you hear me?
Yes, I can hear you.
Thank you, Professor. Could you try to activate your video to see if your camera is working well?
Yes, of course. Yes.
Okay, very good. So we have with us Professor Rokintov. Okay, Professor Karina Navarro is here. Professor Brian Grajales is here.
Hello, hello,
Oh, hello.
hello.
Very good. Also Pedro, right? Okay.
Thank you.
Okay, thank you very much. It's really my great pleasure to give to all of you the welcome to the ICMAM Prize ceremony and to the closing ceremony of our conference. We really have been enjoying this week of the many conferences, of a very nice scientific program, of very inspiring talks, right? But then I think we are just to some minutes to know who will be the winner of the ICMAM Prize, which actually is the most important prize that offer our scientific society. So in order to have our closing ceremony and also the ceremony of the ICMAM Prize, it's really my great honor to inform to the participants that we have with us not only ICMAM authorities of ICMAM Latin America, the international community of mathematicians from Latin America, but also we have with us Professor Tatiana Toro, the Vice President of the International Mathematical Union, and Professor Joachim Toff, President of the International Society for Analysis, Its Applications and Computation, as our invite guest. So thank you very much to Professor Toro and to Professor Toff for being here, for making time in their very busy agenda for this ceremony. And the following will be the plan for the ceremony. First, we are going to hear some words of Professor Tatiana Toro, Vice President of the UMU. Later, some words by Professor Joachim Toff, President of ISAAC. And then we are going to hear from Karina Navarro Gonzalez, President of ICMAM, and from Brian Grajales, Vice President of ICMAM, the name of the winner of the ICMAM Prize, right? So after that, we are going to have some words by Andrea Hurtado, our scientific director in ICMAM, and about information about the in-person program of the ICMAM conference that actually will take place in August by Pedro Fernandez Espinosa, who actually is our new scientific director. So thank you very much to all the participants that are following us. And I would like to invite Professor Tatiana Toro, Vice President of the International Mathematical Union. Please go ahead, Professor Toro.
Thank you. So first of all, good evening and good afternoon to all of you. It is an honor to be addressing the audience of the 2026 International Community of Mathematicians from Latin America, ICMAM Congress. I hope that you all have had a very productive and stimulating week. ICMAM, at the time, the International Conference Multidisciplinary Aspects in Mathematics and Its Applications, was created in 2020 and hosted at the Universidad del Valle in Cali, Colombia. The conference brought together mathematicians across diverse fields, fostering collaboration and sharing groundbreaking research. By 2022, the conference had grown significantly, drawing an expansive community of mathematicians from Latin America and beyond. And from this success was born the International Community of Mathematicians from Latin America, ICMAM Latin America. This is a thriving community dedicated to advancing mathematics in the region. ICMAM works very closely with UMALCA, la Unión Matemática de Latinoamérica y el Caribe, to strengthen mathematical research, foster collaboration, and advance training by bringing together established researchers, emerging scholars, and graduate students from across Latin America. Today, ICMAM Latin America stands as a hub for mathematical innovation and collaboration, proudly showcasing the talent and potential of Latin America's mathematical community. I would also like to highlight the establishment in 2026 of ICMAM Africa to promote mathematical research, collaboration, and visibility across the African country. One of the greatest challenges facing students and mathematicians in Latin America is isolation. ICMAM helps overcome that challenge by creating a space where researchers can exchange ideas, learn about the latest development, and become part of a vibrant mathematical community. As a student at the Universidad Nacional de Colombia in Bogotá many years ago, I would have cherished the opportunities that ICMAM now offers to the next generation. ICMAM promotes the work of researchers across Latin America by providing a platform where their ideas can be shared, their achievements recognized, and their contributions to mathematics highlighted. In doing so, it strengthens the visibility of mathematical research in the region and fosters a greater sense of community and collaboration. I would like to also express my admiration and gratitude to the ICMAM Executive Committee for their vision, dedication, and tireless effort in building this remarkable community. By strengthening mathematics across the Global South, they're not only creating opportunities for individual researchers, but also enriching the entire mathematical enterprise. A stronger and more connected global mathematical community benefits all of us. Thank you very much. And I'd like to congratulate the yet-to-be-known winner of the ICMAM Prize. Thank you.
Thank you very much, Professor Tatiana Toro, for your very kind words. So, it's my great pleasure then to invite Professor Joachim Toff, President of ISAC, the International Society for Analysis, its Applications and Computations, our invite guest for this closing ceremony.
Okay, thank you very much. Can I share a file here?
Yes, Professor. Please.
Okay. So, can you see this, all of you?
Yes, Professor, we can see your presentation.
Okay. Oh, okay. Sorry. Now I see that it should be in the beginning. I just want to put it here. Sorry, I think I made a mistake when I took a note in my calendar. I thought that it should be actually, for some reason, I noticed a Tuesday in one place, and I thought it was the last thing. So sorry for this. So, in any case, thank you very much for having the opportunity to be a part of this closing ceremony of this very important meeting, and I'm so happy to see that mathematics and analysis in Latin America is becoming so strong, and with young talent mathematicians and also a very go in the organization of a lot. So I think this is a important part of the future of mathematics. It will be in Latin America. This is for sure true. And I'm also sad that I couldn't participate in person, on this. So now I see that you cannot see the whole thing here. Just a moment, I will do it like this. Now you can see it better here, okay? Because of this, I could not completely update the file I wanted to have, okay? But so I will talk a little bit about ISAC, and of course, as I said, it's nice to see how strong Latin America becomes, but also I'm so happy to see that we can have this very good collaborations and that we can somehow have a good, I mean, as much as we are able to support these activities from ISAC part, is the for at least ISAC is the other part because ICMAM becomes a really a key collaborator. One can almost say also that big cross-fertilization between our communities and so on. So a little bit about ISAC. This is it stands for the International Society for Analysis, its Application and Computations. And here you can see some important things that appears with ISAC. So a very important part of ISAC is, of course, all the different ISAC congresses that are gathering a lot of people together. Actually, one of the really main ideas with ISAC, of course, it should promote analysis, its applications and computations, the subject of ISAC. But also somehow it was very early, I mean, really from the beginning, it was also that one should try to really connect people, especially from different part of the world, also, how to say, promoting the exchange between, how to say, wealthy countries and less wealthy countries, how to say. So that there was somehow, this was from the beginning, it should not be, how to say, a rich man club. It should more be an attempt to putting bridges between and also, how to say, encourage exchanges between different part of the world. And this is still a cornerstone of ISAC, okay? Beside, of course, well, the subjects. You can see here that so far we have had 15 congresses, and the first one was in Delaware in 1997, and the last one, it was in Astana, Kazakhstan. It is actually the first time it was, they were very proud of having this event because it was the last one, because it was the first, they said, big scientific event in Central Asia. And the next time, I hope that I will have the pleasure to see all of you with in Xiamen in China. But also you can see here, which is really important. Also, I mean, this is extremely important with Xiamen in China, but also extremely important is that 2029, you will see it will be in Colombia. But really, I hope we will meet already in Xiamen, okay? But of course, if we are not meeting in Xiamen, we will for sure meet 2029 in Colombia, okay? Can you promise me that, Professor Cardona?
Yes, sure.
And
I
what
think
about
here
Professor?
we have very good team committed
Yeah.
with that.
And what about Professor Gonzalez? Can you also promise that?
Yes, of course. I
Okay.
promise you.
Okay, very, very good. Okay, I'm very happy to hear this, okay? And here you can also see about in the ISAC congresses, there are several sessions, usually around 15, but it can also go up. I suspect, for example, in China, there might be more than 20 actually, and so on. And there were also a lot of sessions in Kazakhstan in the last ISAC Congress. This is a little bit how is ISAC organized. We have within ISAC a special, so-called special interest group, abbreviated SIG. And here are some of them, but these are not the last ones. I think we have give a little bit more. We have in complex analysis, etc., Clifford and quaternionic analysis. and so on and so on. So there are a lot of different kind of special interest group. Our last one was in fractional calculus, and it seems that we are able to gather into ISAC a big part of the editorial board of the most, how to say, well, I would say, well, they say themselves that it should be the best journal in fractional calculus, a Springer journal, okay? So that's a little bit how it is, okay? And so on and so on. And of course, we enjoy very much when one can have it in such way that you can have some activities within ISAC if you have a special mathematical society. But also we enjoy very much as it works now with ICMAM, that you have really something very huge and lot of activities outside and so on. So this is somehow, one should see this as a platform, okay? So I'm very happy for this very successful conference that you have organized now here, okay? So that's a little bit how it is, okay? Since 2025, we have the officers of ISAC is here, but of course there is then the officers of this society is nothing compared to, especially not the president, if they have not, how to say, a good ISAC board. But of course, this is still not that important as the ISAC members, okay? And I'm very happy to that, well, we have a lot of ISAC members with ICMAM. So we can then have this kind of cross-fertilizations. So that's a little bit about that, and so on. And also we have book series and ISAC associated journals. And we also have ISAC news that we distribute to the members 2 times per year, and so on and so on. So that's a little bit. And at each ISAC Congress, also in similar way as here in ICMAM, we give so-called ISAC Award to a young, outstanding researcher. And also we have, well, these are some recent awards. This is not an updated, I wanted to update this because we have some very nice awards also recently, but so and so on. So we give it, the last one was given 2025 in Astana. And so on. And so on. You can also see some of these people perhaps you recognize, for example, Michael Roshansky. He's, I think you have encountered him, what do you say, Professor Cardona? He is not so inactive, yes, that's true. And also some others somehow. You can also see Terence Tao, for example. So on and so on. So if you are not an ISAC member yet, you are very welcome to become one. So you just contact one of the officers, and hopefully one can then, this can also hopefully be helpful for ICMM MAM. I believe that we can both make us stronger together, how to say. So thank you very much for having the talk, and really I wish you, how to say, well, I would say that it was so good conference, and also I'm feeling confident that your next conferences, and also especially when you organize the next ISAC Congress, will be very successful. So thank you very much for your attention. This is just thank you for attention, okay?
Thank you. Thank you very much, Professor Jakintoff, for your very nice presentation. Just a comment. In the next ICMAM Africa, actually, Professor Jakintoff is one of our plenary speakers. So I really invite all of you to follow Professor Tov plenary in October. So, okay.
Thank you very much.
Okay, so then now it's time to know then who will be the winner of the ICMAM Prize. And for this special moment of our scientific program, I invite Karina Navarro González, President of ICMAM, and Professor Brian Grajales, Vice President of ICMAM, who will give us the name of the ICMAM Prize winner.
Okay. Hello, everybody. So we will start with my speech. So, ladies and gentlemen, on behalf of the international community of mathematicians from Latin America, I am honored to present the ICMAM Prize 2026 to Professor Maria Jose Pacifico. I would like to begin by thanking her for accepting this distinction and for joining us on this occasion. The ICMAM Prize recognizes scientific achievement. It also recognizes work that has contributed to the development of mathematics in Latin America. Professor Pacifico's career gives us a strong reason for honoring her in both respects. In honoring Professor Pacifico, the ICMAM Prize continues its tradition of recognizing outstanding Latin American mathematicians. Following previous recipients, Tatiana Toro, today here with us, and Carlos Kenning. Maria Jose Pacifico was born in Guariba, in the state of São Paulo. She completed her degree in mathematics at São Paulo State University, USP, in Rio Claro, São Paulo State University in Rio Claro, in 1973. She then continued her studies at the Institute for Pure and Applied Mathematics, known as IMPA, where she received her master's degree in 1976 and her doctorate in 1980, under the supervision of Wellington de Mello. After completing her doctorate, she held a faculty position at Fluminense Federal University. In 1982, she joined the Federal University of Rio de Janeiro, where she has spent most of her academic career. She became a full professor in 2006 and has remained closely involved in research, graduate education, and university administration. Her publication record was already notable in the early 1980s. By 1984, her work had appeared in Invention Mathematicae, the Journal of Differential Equations, and Ergodic Theory and Dynamical System. In 1986, she published in Topology and again in Inventions Mathematicae. These early papers began a research record sustained for more than 4 decades. Professor Pacifico is internationally recognized for her contributions to the dynamical systems. Her main areas of work include flows with singularities, Lorentz type attractors, partial hyperbolicity, and entropy. Her results have become an important part of the literature on dynamical systems, and she is widely recognized for her major contributions to the development of singular hyperbolicity. The formation of students and young researchers is another important part of her work. Her updated academic records list 16 completed doctoral theses, 14 master's dissertations, and 31 postdoctoral researchers under her supervision or joint supervision. This number represents many years of reading, discussion, and individual attention. A number of these researchers later became her co-authors and continued their own academic careers. These aspects, if her work deserves the same attention as her publications. A mathematical community depends on researchers who are willing to train others and to help them develop independent work. Professor Pacifico's activity as an advisor has extended her contribution well beyond her own articles and books. She has also taken on demanding institutional responsibilities. At the Federal University of Rio de Janeiro, she coordinated the graduate program in mathematics from 2012 to 2017, and again from 2022 to 2024. At the national level, she served during 3 separate periods of the Advisory Committee for Mathematics and Statistics of Brazil National Council for Scientific and Technological Development. Her service has also had an international dimension. She has worked on committees of the World Academy of Sciences, including panels responsible of the selection of awards and new members. She has also contributed to regional programs of scientific cooperation in mathematics. Her scientific standing has been recognized by major institutions in Brazil and abroad. She received her first Research Productivity Fellowship from Brazil's National Council for Scientific and Technological Development in 1981. She currently holds level 1A, the highest category in that fellowship system. She has repeatedly received the distinction Cientista do Nosso Estado, award by the Research Foundation of the State of Rio de Janeiro. She was elected a full member of the Brazilian Academy of Sciences in 2005 and became a member of the World Academy of Science in 2007. She was also awarded the rank of Commander of Brazilian National Order of Scientific Merit. In 2024, the Brazilian Mathematical Society, the Institute for Pure and Applied Mathematics, and Brazil Ministry of Science, Technology and Innovation awarded her the prize Elas na Matemática in the category Outstanding Scientist in Mathematics in Brazil. This award recognized an established scientific career and her role as a woman in a field in which positions of research leadership have long been occupied mainly by men. This part of her history should be stated directly. Professor Pacifico established herself through the quality and consistency of her work. She later occupied a position from which she could participate in decisions affecting mathematics in Brazil and abroad. The ICMAM Prize 2026 recognizes the quality of Professor Pacifico research. It recognizes her sustained work across more than 4 decades. It recognizes the students she has trained and the responsibility she has assumed. It also recognizes her place in the history of women in mathematics in Brazil and Latin America. Professor Maria José Pacifico, thank you for accepting this award. Thank you for your work, for your contribution to the education of new mathematicians, and for your service to our scientific community. It's my honor to present you with the ICMAM Prize 2026. Professor Pacifico, congratulations.
Thank you. Can you hear me?
Yes, I can hear you well.
No. Thank you very much.
Okay, now I think the connection is in the best
I
way.
sincerely,
Okay.
Okay. I sincerely thank the ICMAM Award Committee for selecting me for this distinction. I also wish to share this recognition with my many co-authors and collaborators indeed. Throughout my career, they have been essential in shaping my mathematical journal. And this award is, in many ways, a recognition of our collective work. I have greatly enjoyed this conference. Unfortunately, I could not attend all the talks. Still in progress at my university, and this is the busiest time of the year for us. Even so, I found the conference truly inspiring. It brought together outstanding researchers from a wide variety of mathematical areas, creating an exceptional scientific atmosphere. I also was delighted to see such a good balance between women and men among the invited speakers. As someone working in dynamical system, I was especially pleased that our field was represented as well. And I believe that meetings like this play an important role in strengthening mathematics developed in Latin America, increasing its international visibility and fostering collaborations that will have a lasting impact, no? And then thank you once again for this great honor, and a great thank you to all for Professor Cardona and all the others involved in the committee here. Thank you very much. I'm really honored to receive this award. Thank you.
We have some comments on YouTube. Everybody's congratulating Professor Pacifico for the prize.
Very good feedback from our community. So thank you very much to Karina for the speech, and congratulations, Professor Maria Jose Pacifico, for this prize. It's really an honor for us to have you here. And thank you for accepting the prize, of course. So let's continue with the closing ceremony. I would like to invite Andrea Hurtado, Vice Scientific Director of ICMAM Latin America,
Hello.
to share some words with us. Please, Andrea, go ahead.
Hello, everyone. Good afternoon. Before we conclude this wonderful conference, I would like to share a few personal words. Being part of the ICMAM Latin America community has been one of the most rewarding experiences of my academic journey. Over the past 3 years, I have had the privilege of participating in different ICMAM initiatives, from the Humalca ICMAM Latin America seminar to the Women in Mathematics projects and the ICMAM Young Researchers program. Through these experiences, I have met remarkable mathematicians, collaborators, mentors, and above all, wonderful friends. A few months ago, I had the great honor of being appointed Vice Scientific Director of ICMAM Latin America. Receiving this invitation was both humbling and deeply meaningful to me. To be entrusted with this responsibility while I am still pursuing my PhD is an honor that I do not take lightly. I am sincerely grateful to the Executive Committee, to Professor Karina Navarro Gonzalez, Professor Brian Grajales, Professor Duan Cardona, Pedro Fernando Fernandez, and everyone who believed in me and gave me this opportunity. I completed my bachelor degree in mathematics in Colombia, and in 2017, I left my country to pursue my master's degree abroad. Since then, every year has brought new challenges. Building a scientific career in a foreign country is not always easy. It means adapting to new cultures, new languages, and new academic environments while being far from your family and everything that once felt familiar. Looking back today, I feel incredibly grateful. This appointment reminds me that dedication, perseverance, and genuine passion for mathematics can open doors that once seemed impossible. Throughout these years, I have learned that challenges do not define us. Our response to them does. Wherever I have been, I have tried to face every obstacle with resilience, hard work, and the determination to keep learning and contributing to our mathematical community. Those are values I will continue to carry with me wherever my career takes me. I would like to thank all the speakers, participants, organizers, and everyone who worked behind the scenes to make ICMAM Latin America 2026 such a success. Your dedication and enthusiasm are what make this community so special. If there is one message I would like to leave with our students and young researchers is this: do not be afraid to dream beyond your borders. Your path may not be easy, but with perseverance, integrity, and hard work, opportunities will come. I am standing here today as proof that they can. Finally, I encourage everyone, especially our students and young researchers, to stay connected with ICMAM, participate, collaborate, ask questions, and support one another. Together, we are building not only a stronger mathematical community, but also a community where people can grow, belong, and inspire one another. Thank you all for making this journey so meaningful. Thank you very much, everyone.
Thank you very much, Andrea, for your very inspiring words. Then I would like to invite to Pedro Fernando Fernandez Espinosa, our current scientific director, who actually then is the director of ICMAM Latin America in Colombia, has a research group there that actually is affiliated to the Minister of Science and Technology of Colombia. So please, Pedro.
Thank you, Duan. Thank you, everybody. Can you hear me properly?
Yes.
Okay. I just want to start by saying that I am very happy to be here. I am very, very happy to be part of this very wonderful team of friends, I think. And I also want to say that words cannot express how happy I am and how honored I am to be part of this community. And also, I think words cannot express how happy and honored we are to have organized this meeting and have this wonderful week of mathematics, and share with this very beautiful community, not only in Latin America, also around the world. I would like to also thanks again to our speaker for their time, for their disposition with us. Also, I would like to say thank you for all the participants of our conference. Without them, I think nothing has sense. And now this is the end of one of the stage of this ICMAM 2026 conference. Today is the marks the conclusion of this part of ICMAM, but this is not the end of our conference. in August, I would like to say that we have a second stage of ICMAM 2026 conference. Will be in person, and which will take place in Duitama, Boyacá, Colombia, which is now my place. And I would like to invite all of you to participate in person. In that moment of our conference, we will have plenary talks, some courses, and also some contribute talks, mainly by students, undergraduate, master, and doctoral students. So if you want to join us, you are really welcome. If you want give a talk, just please feel free to contact us. And we are very happy to receive hearing in this beautiful town in Boyacá. And I think that's it. I am very happy today. And I also, as Karina and also as Andrea mentioned, I'm very happy to be part of be part of this beautiful team. I consider all of you my friends, so I am now very, very happy to be here. So thank you very much, and see you in August here in Boyacá. And thank you.
Thank you very much, Pedro, for the invitation to follow in the next in-person program of our conference in Duitama, in Boyacá. So, Professor Tov, if you want to visit Colombia, you are welcome to visit Boyacá,
Okay.
for the in-person program.
Thank you very much. I would like to, but we will see there is some distances, etc. So it's not the closest place for me. And it's,
Otherwise, you have second opportunity in ISAC 2029.
yeah, that's true. That's as well. But thank you very much for the kind invitation.
Thank you very much. So with this, then we finish our scientific program of the virtual conference, and thank you very much to the participants that have joined the sessions. So thank you very much. With this, then we finish our conference for this week. So see you in the in-person program. Thank you very much.
Bye, bye, bye.
Bye-bye.
Bye-bye. Thank you. Many thanks. I'm quite honored
Bye-bye.
by
See
this.
you. Obrigado. Gracias.
Professor Cardona, please write in the chat for the meeting in August the name of city, because I could not understand it. You talk in a Spanish accent. Do you understand?
The name of the cities.
Yes, yes. Yes, we are going to have a program in August.
Pedro Fernandez, yeah. What is the writing in the chat, because I cannot understand it when you talk in Spanish. I don't know.
Duitama. Boyacá.
Duitama. Yes.
Boyacá. Okay, thank you.
Okay.
Now I understand. Thank you.
Brian, maybe we
Thank
can
you
finish
very
the
much.
streaming. Maybe.